Hello, good evening, sir. Hello, good evening, sir.
Hello. Good evening, sir. Where is sir?
Sir, good evening. Sir, good Kasim sir, Kasred sir, good evening.
Yeah, good evening, sir. Welcome, sir. Yeah, good evening, sir. Welcome, sir.
Okay, sir.
Kasireddy sir, can you hear me? Kasim sir,
Yes, madam.
shall I start,
Audible,
sir?
ma'am. Audible, your voice audible.
Okay, sir. Okay. Where is it?
Yeah, dear participants, be starting within 2 to 3 minutes.
Okay, sir.
Hello.
Hello, sir. Dr. Ravindra, sir.
Yeah, hello, sir. Good evening.
Audible, sir. Yeah, yes, sir. So we are making a presenter, sir.
Actually, your voice is breaking, sir. Hello.
Hello, is it audible, sir?
Sir, your voice audible, sir.
Yeah, it is audible, but noise resound is coming. Yeah.
Oh, okay, sir. Okay, sir.
Yeah, yeah.
Yes, sir. Okay. Sir, now please check, sir, whether voice is audible, no, sir, clearly.
No, sir. Actually, noise is coming a lot, sir. I don't know.
No, sir, voice is not coming, sir.
Oh.
Hello.
Hello, sir. Yes, sir. Yes, sir. Your voice is audible, sir. Is it still
But,
still it is unclear, sir?
No, sir. It is not clear. I think a lot of.
Sir, the slide and the picture is not visible.
Hello.
Sir, yes, sir. It's not visible, sir.
Actually, your voice is not audible clearly, sir. Am I audible clearly, sir? Is there any
Yeah,
noise?
your voice is very clear, sir. Very
Okay.
clear.
All right. Okay. Then let me share my screen. Yes, sir.
Yeah, sir.
Yes, sir, now it is audible, sir. Now it is audible.
No,
Now
it
it
is
is audible, sir.
lot of noise is coming from your end. I think maybe because you are using some mic. I think that is giving them. Anyway, pretty fine. Sir. I think my screen is visible, right?
Yeah,
The
your
screen also
is
visible, sir. Yes, sir. Yes, sir. Yes, sir. Please.
All right. Yeah.
Okay, I'll introduce, sir.
Yeah. Shall we start, sir?
Sir, please wait, sir.
Yeah.
We'll be taking some 1 to 2 minutes for introduction, then
Sure.
later then please continue, sir.
Sure.
Good evening, everyone.
Wait, madam. Please wait,
Okay, sir.
madam.
Okay, sir.
A very good evening to all the esteemed speakers, respected faculty members, and enthusiastic participants joining us today. So, we on behalf of Vishnu Institute of Technology, Bhimavaram, warmly welcome you all to day 4 of our Atal FDP program on emerging trends and future prospects in advanced energy conversion technologies and applications. So over the past 3 days, we have explored key dimensions of powertronics from electric vehicle systems and microgrid converters to energy policy and SRM drives and solar PV power conditioning systems. So thanks to our distinguished experts from IITs, NITs, and the Central Authority, Electricity Authority, and from ORF America. So today we'll continue this learning journey with two highly technical and exciting sessions focused on solar PV powered converters for electric vehicles and also the real-time power system monitoring using PMUs. So both essential pillars for smart and sustainable energy infrastructure. So I'm delighted to welcome back Dr. Ravindra sir, Assistant Professor of MNIT Allahabad, who conducted a wonderful session on the first day of our FDP, which is on solar PV condition systems for green energy. So I request Professor M. Lavanya Madam to please introduce our today's resource person. Over to you, Madam.
Okay, sir. Good evening, everyone. I'm M. Lavanya, working as an assistant professor in the Department of EEE at Vishnu Institute of Technology, Bhimavaram. A warm welcome to all the participants joining us for this evening session of the FTP. Today, we are once again honored to have with us our distinguished resource person, Dr. Dagga Ravindra, Assistant Professor in the Department of Electrical Engineering at Motilal Nehru National Institute of Technology, Prayagraj. As many of you know, Dr. Ravindra has a remarkable academic and research background in power electronics for electric mobility, renewable energy systems, wide bandgap based power converters, solar PV systems, microgrids, and smart energy systems. In his previous session, he shared deep insights into solar PV fed converters for EVs using simulations, which was truly informative and appreciated by all participants. We are delighted to have him with us again today to continue this intellectual journey with his talk on solar PV power condition systems for standalone applications. Now, we extend a very warm welcome to you, sir. We request you to kindly take over the session and enlighten us with your talk. Thank you.
Yeah, thank you very much, ma'am, and thank you very much, sir, and thank you very much for all the coordinators for again giving me a chance to present some of my work today. And very good evening to all the participants. So before further proceeding further, so let me share my screen. I think my voice is clear, no, sir?
Yes, sir. Very clear, sir.
Okay.
Very clear, sir.
Yeah, thank you, sir. My screen is visible, no, sir?
Yes, sir. Visible, sir.
Okay, sir. Thank you. Yeah, so yeah, very good evening to everyone. So today in this session, we are going to discuss about power conditioning systems for standalone PV applications. So we are going to deal with a lot of power electronic converters, means to act as a power conditioning unit for to extract the power from solar. Okay. Most of these topologies I'm going to discuss various power conditioning units and whether they are suitable for. We have two types of systems, like in case of a solar, one is the standalone and second one is a grid connected. Okay, so I'm going to discuss in detail about various power conditioning units and we are going to see their various features. Okay, if you go through the literature, there is a lot of power conditioning units are there for extracting the solar PV power that is applicable for standalone, as some are for grid connected. Some are like some topologies, they are very suitable for both the applications. Okay, so we'll see them in this coming in this session, coming 1.5 hours. So if time permits, we can also see all these topologies. What I'm going to show you, I have simulated them, and most of them we have validated using some kind of experimental setups. Okay, so and also we can see how we can enhance the performance of such solar power conditioning units. Okay, so we'll see this. This is the and before further, like I wanted to say you that I have we have developed very high power solar PV power conditioning unit to extract the. You can see that it is a 200 kilowatt silicon carbide based converter. This is the load, like RL load we are having. So right? We have this is the load. This is the power supply, and here our converter is there. I will show in the next slide. Okay, these are like you can see this very beautiful power conditioning unit we have developed at 200 kilowatt power. Okay, with 99.3% efficiency. You can see that it is that they have very good efficiency. We have, since these power conditioning unit means power electronic means solar PV inverter, we have developed with the help of silicon carbide devices. This work I have done at North Carolina State University during a few years back. Okay. Driving the silicon carbide device are very tough, challenging even than today, like at this much high power level. But yeah, we have successfully validated and we have successfully extracted the power in the solar PV. You can see these are the drivers and this is the converter. You see that it is very beautiful, very small converter. You can see this. We have compared with various power semiconductor. Like, see, we wanted to develop 200 kilowatt solar PV system. Let us take it. So we wanted to have this much high power. With silicon, you have only one option in the market, like 1200 volt, because we wanted to make 800 volts DC. Generally, like 200 to 1000 volts, we have to make a power conditioning unit that should accept the voltage in this range, right? And it has to provide the required voltage and required power as per the load demand by extracting the maximum power. So we'll see that if you want to develop this much high power, so you can see that this is with silicon, but this is a IGBT. You should note that this is a IGBT, because with the silicon you can understand that with MOSFET you will not be able to get the devices at this much high power, right? So, but in case of these are the SiC MOSFETs, okay. These SiC MOSFETs, you can see that even at a MOSFET, they are handling very high voltage and high currents. You can see that, okay. And you see that the losses, you can, as you know, that this green one is our this green one is a IGBT of SiC, okay, silicon IGBT, and rest all other devices, as I mentioned, they are silicon carbide devices, okay. As switching frequency is increasing, you can see that the losses are drastically changing in case of as silicon. These are the like losses, right? So against the switching frequency, you can see here the efficiency. Okay, so as I said that you will be able to meet. This is including all the losses, right? We are finding out the efficiency. It is almost like 98 point. Only if you see the devices are having 99.3% efficiency, but as a system level, it is able to give almost like 98.8 in this with this module. And some of the key devices, because there you can see their on state resistance changing and also their on losses and off losses. This is like on state resistance, and these are the from the we have also characterized these devices. We have found we have done we have found the on-state losses and off-state losses by characterizing the devices at various operating points. And then can see, as I said, that like in case of IGBT of silicon, it is giving 93.3%. But whereas you can see, we are getting almost like 99. Even you take 93 to 99, I mean 6%. Even you take a 5% difference, it is giving a huge advantage. Okay, if you see the economics, right? Let us take, you wanted to make a 200 kilowatt system. Well, let me give you some calculations here. Okay, so you wanted to make a 200 kilowatt system. Okay, with SI means silicon IGBT, you will be able to do this much big power conditioning unit for this high power. Yeah, another side you are going with silicon carbide MOSFET. Okay, so in case of silicon carbide MOSFET, and the difference I said that it is like 5% difference. Okay, 5% difference means you are able to extract 10 kilowatt power more, right? Let us take it is 98%, right? And it is, let us take 93%. Okay, so in this case, how much you are going to get is that to 186, and in this you are going to get 196 kilowatt, right? Output power. Okay, with this much efficiency we are talking. Okay, so it means almost the 10 kilowatt difference is there, right? Means you are going to extract more power with this silicon carbide based power conditioning unit, right? So let me take another color. Okay, so when this is like you are able to extract more power in case of these SiC devices. So in 1 hour, you say that you are able to have 10 units more. You will be able to means you will be able to get more power, 10 units per hour, right? So 10 units, right? So in a day, you are going to get like 240 units. Okay, hey, this is like this much high power means it is industrial customer. You say that per day. Okay, so you are able to uh, produce more to 240 units in case of a SiC, right? 240 means like it is a industrial customer. This much high power means even you take a unit cost around 8.5 rupees. Okay, so you can see that you're going to save almost like 2000 rupees per day. Okay, I'm just doing a rough estimation, so I'm not doing exact calculation. So, like per day, you are able to generate this much high power compared to the silicon-based devices, right? Per day, this much means monthly. You can say that you are able to produce 60,000 rupees high power means, and then in a year you are almost like 7.2 lakhs. Okay, so even you take a inverter life is almost like you take like 4 units, 4 years. Then if it is more than 4, is also we'll be having some kind of power conditioning units with high reliability. Maybe latest, even worst case, you take a 4 years. It's almost like 28.8 lakhs you will be able to save. Okay, so means you are going to get more revenue with these SiC devices compared to this SI based IGBT. That much benefit is there. If you take if you take the cost initially, this is like high cost. Even like that time when we have calculated, it is like almost costing around 8 lakh. There the difference is 5 lakh, 4.5 lakh, something like that. Okay, so initial investment is slight high, but you see that how much you are able to save more money in this case. So this is highly beneficial, but people they will think that okay, initially when they are buying it, okay, silicon based inverter you are getting at almost like 4 lakhs lesser price. So that's why they prefer this. But since now these wideband gap devices based converters are not that much popular like silicon, because silicon technology is there from several years, but silicon is like we are in the now wideband gap era. So that's why the large number of players are there in silicon. So there's a lot of competition. That's why the prices are down, and there is huge production is there for silicon. That's why the prices are low. But in coming few years, like coming 5 to 10 years, the silicon carbide market is also a lot of players are coming, and then the prices even. So even wait, what I wanted to say. At initial stage itself, their prices also becoming low, and then you are going to get this much very high economical benefits if you are going for highly efficient power conditioning unit. Okay, as you said earlier, this is the the beauty with the wide bandgap devices based power conditioning units. Okay. Apart from there is several other advantages also there. We'll discuss that. That is on the device level, device side. But anyway, our topic is here is power conditioning units. Right? So, like before going further, first you should understand what kind of PV systems are there, and now we are focusing on standalone, means off grid, right? So we see that how we can make what are the topologies are suitable for this off grid and all this. Okay. So basically, like solar PV systems are two types. One is a grid connected system, or second one is an off grid system or the standalone system. Okay. So here in the war, like most of the more than 90 to 95% systems are grid connected, and 5% systems are standalone. Okay, that is what the survey says. This is from MNRE. The statistics. Okay, so now we are going to see the power conditioning structure. Okay, there is a two ways you can extract the power from. In case of conventionally, we can extract the power. In case of solar, in the classical way, the people, the power conditioning unit manufacturers, they are designing it like what they do. They have some kind of a DC-DC converter, and then they use a inverter to power the load, right? So in another way, with that single stage inverter is also becoming more popular nowadays. Like there is a various classifications are there, like central inverter, string inverter, multi-string inverter, and then module inverters are there. Depending on that, you need to take one of these structure. We'll see that. Whatever may be the structure, you will be having the role of power conditioning. Hello. Yeah. The role of power electronic, this power conditioning is that it should be taking care about this MPPT tracking, and then DC to AC power conversion, because you are going to use your power in case if you want to power the AC load, and then voltage boosting, because our PV module at module level the voltage ratings are calculated. Okay. So in case of two-stage power conditioning system, as I said, that it is very popular. But in this two stage itself, there is a two ways you can extract the power. What is that? Here I kept the simulation waveforms. You can see that this is the, let us take, I have taken a 100 volts module. And then I'm making a 400 volts DC step DC, and with MPPT, we are operating this DC converter. Means it is stepping down, stepping up, as well as it is taking care about MPPT. And then this one is this DC is being converted into AC. These are the results, the simulation you can see. Another way, this is the classical approach we generally do follow, means solar PV and then constant DC and then PWM inverter, then you are going to give it to the load. Okay, maybe grid or load. Okay. Another way is that what you can do is that you have this kind of 100 volts, so let's take 100 volts DC. Okay, so what you can do is you can also generate this kind of rectified type of this kind of DC you can able to convert with the help of this kind of DC. And we can see here I kept the results. You can, and then what we do is that simply you try to use inverter to just to change the polarity. Okay, so this is another way. Yeah, this is another way of meeting the requirements from the PV module, right? Then this here, the beauty is that this inverter no need to operate at a very high switching frequency. It just it has to two switches will be on for this period, and then another two switches will be on for this this period. Means they are not operating at PWM. So when they are not operating at PWM, switching losses quite low here, and switching losses are quite low. Then what will happen? Their efficiency is better. Okay, in this case compared to this, but why then you would have, then you immediately we get a doubt that why this is not popular. As I said, that this is very classical. The reason is that here you can easily understand that we are having a DC. Okay, so we are stepping up and we are trying to produce a rectified natured DC, right? So when we are doing it, then you will be needing because the average values will be like, let us take rectified natured DC, average value is like 2m by pi is equal to let us take average value. Okay, so you see that your peak value is too much higher than the DC value. That means this peak value was very higher than your average value. Average value will be somewhere here, but your peak values will be this much, right? So what happens is that whenever you design this converter, you need to in this case you need to size all the components for the DC values, but in this case you need to size all the components for these peak values. Peak values are higher, right? So means you need to have the whatever inductor, capacitor, switches, and diodes, the slightly you need to go, you need to design for the higher rating that will give the size, cost, value of the converter. That's why, although this is one approach where you wanted to reduce the losses of this second stage power converter in a power conditioning unit, then people will prefer this. And another side, okay, give me a moment. Okay, the first approach is more classical and conventional.
Sir, your voice is low.
Hello, am I audible now?
Yes, sir. Yes, sir. You're audible, sir. Please continue, sir.
Okay, thank you. So yeah, so like this, there is a two ways you can extract. You can build your power conditioning unit, which is very responsible for MPPT, and then stepping up the voltages and then inversion, and then you need to fulfill the requirements of this AC load, right? We'll see that there are like in whether it is a single stage or two stage power conditioning unit, you need to have this inversion feature, right? Because we have most of our loads of AC type. Okay, so since we have adopted a universal power generation is AC, so that's why we at the end we have all kind of loads are available for AC. That's why this inverter is very much essential, and right, whether it is either it is a two-stage power conversion or single-stage, the inverter plays a vital role, and this has to this power conversion by power conversion unit. It should be able to provide desired voltage and frequency. It may be either grid or standalone. Okay, and you need to maintain very good power quality as per the required standards. Whatever, like I will show you the standards also. Our power conversion should be able to meet the standards imposed by the respective countries. Each country is having a different standards they do follow. Okay, countries like US, Germany, Europe, and then Japan, they do follow very strict standards, regulations. So we need to fulfill them if you wanted to go into all the all countries market. Right, and also able to have a proper electrical isolation with the DC from electrical power under abnormal voltage, current, or frequency conditions. Okay, and your control of DC should have ability to perform. Let us take if you have a two stages, then there is no problem. But you're having only one stage power conditioning unit, there should be able to taking care about MPPT, voltage control, current control, active power, reactive power, frequency control. A lot of features you need to incorporate it. Right, we will see that, and also as I said that you need to have a proper active and reactive power control, etc. Okay, and apart from that, we need to take care about the like THD and individual harmonic current levels and power factor requirements and offset inject some DC, some kind of a power conditioning units. They also inject some kind of offset DC current. Should be there is a limitations regulations on that also. Like there is a special standards are there VDE like from the Dutch means from Germany. They also strictly follow this kind of and the DC offset currents also. Okay, the voltage and frequency range for normal operation and detecting island and automatic reconnection and resynchronizing and proper grounding, some kind of some topology they do not allow your PV as well as load to ground. Okay, we'll see that. Even you take a simple inverter, that voltage source I hope most of you people guys are very much popular with voltage. So let us take simple for understanding. Let us take, I have my PV module here. It is like a DC, and then here I have a simple inverter. Okay, so here I have just put some kind of L and C filter, and then because I wanted to produce a pure sinusoidal, right? And then you see, if you wanted to put this one here ground, you will not be able to keep the ground here, because if you are both are grounded, then what will happen? This is like you will not. These 2 points of the switch is having the same potential. That not allows. Some topologies they do allow, because in case of solar, if you see in terms of safety standards, okay, safety standards, some most of the trees, they are also having a restriction that you should not have a PV module voltage should not be more than 100 volts. Okay, and that is the one requirement. And also if it is more than 50 or 60, some countries they do follow that. Your PV negative terminal, okay, should be grounded, and also your load side neutral should be also grounded. Okay, that kind of standards are there. Okay, to meet the very good safety. Okay, so anyway, like we need to fulfill, if you want this kind of features, as I said, the conventional inverter, they do not able to provide this. Okay, if you have some kind of a transformer or something like, then it's fine. But if you're not having transformerless topologies, then you need to have this kind of a feature, dual grounding, and then proper, and also DC offset current injection. All these things, they are very much critical, and also we'll see that. Okay. So as I said that, like a lot of countries, they do follow different kind of standards. Anyway, I'm not going too deep, but everyone should know that what are the requirements before going to the design of power conditioning units, means for voltaic inverters, right? So okay, so in like what is the voltage range, and then what is the harmonics, like standard DC offset injection. I read that in India also we do follow less than 0.5% of the full rated current. That there should not be more than this. If it is that, your inverter design will not be accepted, right? And this is the frequency range, and then we are following this anti-aliasing IEEE standard. Like that, also PV side, also different countries, they do follow different standards for different types of PV modules. Okay, and then renewable energy meters, and then we have such product like SCADA, right? And then like different each device which you use it for solar PV, they do follow different countries follow different standards. One should go into deep into these standards, okay, and then you will be able to fulfill these requirements. Then only your inverter, converter, or whatever you design, that will be allowed to release into the market. Okay, we need to get a certification. Okay, so like I wanted to also bring into your attention that most of these either inverters or power electric inverters for solar, they all are not from made in India. Okay, so you see that most of the market like is 30.6. This is the, as I said again, it is from Ministry of Renewable Energy, New and Renewable Energy. From the data I've taken, can see that most of these suppliers are SMEs, not Indian manufacturer. This Bonfiguli is also not ABB, Power One, Schneider Electric, ACE. These all are like non-Indian manufacturers. That's what, if someone is able to make some kind of a very good power conditioning system, then there is a huge advantage is there. Huge market is there in India, so you can grab easily market. Okay. So, like what country, what are the different manufacturers that do follow all the standards? Okay, that I just put it here. So, mostly these ABB and Power One, SME, and all, and even Sucum, they follow most of the features, but some they are not having this kind of a features like LVRT frequency regulation and all, and they're also trying to incorporate all these things in their next revision. As I said that, like when we are having different configurations like central inverter and then string inverters and then multi-string and then AC module. There is 4 types of inverters, whether it is standalone or grid tied. Okay, so we say that you are keeping a inverter for all the PV modules you have connected them in series or parallel to get your desired power, and you will be having your inverter at a central level. Okay, so this is like typically we use it for very high power. That's why we say that it is a 3-phase. Okay. And the next configuration we have, this is a string inverter, and then multi-string, and then module. Okay, so you say that in case of a string, each string we have a dedicated inverter. Okay, so you see that for each. In case of a multi-string, okay, each string is having a DC-DC, and all these multiple strings is having a single inverter. Okay, in case of central string, multi-string, you have several PV modules. You have connected them in series to get your desired voltage. But in AC module is a very special case. Like you see, at a module level, you will be having maximum 60 to 70 volt. Let us take 70 volts module you are having, but for the load you need 230 volts, right? Let us take you have 50 volts module, then you almost need 5 times gain. Okay, even let us take, as I said, that you're having a voltage source inverter. Then if this inverter, what it will do, it will only step down, it will not be able to step up. So in that case you need, let us take 400 volts DC, and then you need to have 8 times gain DC-DC converter. So that is classical, that is not possible with a classical converters like boost and all. Theoretically they can provide infinite gain, but practically will max, like mostly will go 4 times or somewhere around 4.5. If you are going above that, then your efficiency drastically decreases. That's why typically we do 3 to 4.5, something like that, not more than that. But in this application, you see that we have a requirement of 8 times gain. So there is a special topologies are there that is typically we need to keep it for this AC module inverters. Okay, we'll see. This is like each module in AC module inverter means you have, also we say micro inverter. This we have another name, micro inverter. You would have had this name like micro inverter. In case of micro inverter, what we have is that we have for each module we have a dedicated power conversion unit that will be able to provide you required AC. Since these modules you are having up to like 350 watts or for 400 watts module, right? So this single phase, mostly your output is for single phase, right? You are not having that much power to go for the 3-phase. These are the, like whatever I told, the advantage and disadvantage I kept it here. Now whatever we are going to discuss first, all these power conditioning units, we are going to see what we are having, whether they are having standalone feature or not. And then we are much interested in standalone. That's why we'll see. And also, I like some topologies. They are dedicatedly for standalone. Some are like, most of them are useful for both the grid connectors as well as the standalone applications. We'll see this. And whether it is having isolation or not, we'll see. And it is having proper decoupling or not, we'll see. Okay, and we will see that whether it is for single stage, 2 stage, or 3 stage. And as I said that there's a requirement of dual grounding and then power handling capabilities. We'll check whether they are suitable for low power application or medium power or high power. Component, we'll see how many components they are using it, and then what is the size, wide range. At the end I will show you a lot of topologies now. And then we'll see at the end comparatively, some are suitable for string architecture, some are suitable for central, some are suitable for multi-string or module, or some are suitable for standalone, some are suitable for grid connector. Like this we can see. And also the cooling requirement and wide range of operation is there or not, symmetrical operation in both the cycle is there or not, and then filter requirement on AC is there or not to meet your desired power quality standards. Okay, and the complexity level of control strategy is complicated or easy. We'll see that step by step. Okay, so these all topologies like power conditioning units, they have been classified into multi-stage and then single stage and right. More than two, we say it is a multi-stage and then single stage topology. And at the last, I will also show you the three-phase. Okay. Mostly these are like multi-stages, typically based upon DC to high frequency AC and then DC and then AC. Okay. At then we want AC with DC link and then pseudo DC link, and then another way is the DC to high frequency AC and high frequency to low frequency AC. This is the classical topology which we have discussed earlier, DC to DC and then DC to AC. And in single stage, there is a various configurations. They have been derived with the boost inverters, buck boost inverters, buck inverter, cuck inverter, Zeta, and other are based upon classical DC-DC converters. Like they have tried to derive the inversion also. Like it can stepping up and stepping down. We say it is a buck boost inverters, and only stepping up only it is a buck inverter. Like that. We'll see that. Okay, so these are very classical. In initial days, this was proposed by the company GE. Okay, it is not directly like in around 1990 somewhere. They had developed this topology not only for PV, it is also they have applied to the wind. Okay, with the wind they have developed DC link, and then they have used this structure to okay, to meet their desired load. Okay, so you see, as I said that has all the topology which I'm showing, I kept the simulation results, and also with the color coding, you can easily understand which are the switches they are simultaneously on, and how what is the at the different stages, what kind of nature of either AC or DC are getting. You can easily. I have made this. Circuit diagrams with very much self-explanatory, and you can easily understand by seeing the topology and by seeing the results. You can see that these devices are operating at PWM. You can see that these are PWM, and what we are having this is a DC. Okay, this is coming from PV module. Okay, and then we need to have some kind of a capacitor at the input side to reduce the ripple current, and then proper decoupling can be done with this, and these two switches, the green color switches are turn on together and turn off together, right? And this blue color is complemented to the green, and they do operate when this green is on, blue will be off, blue is on, green will be off. These are operating at a high switching frequency. Then you will be able to get here very high frequency AC, and then this high frequency low voltage AC is converted into stepping up to 1:n, depending upon your desired amplification. You put your transformer trans ratio, then you can step up to your desired level of DC, and then with the help of this rectification diodes, okay, means this bridge rectifier, you will be able to convert into the DC. And then we have a filter over here. This is the DC link capacitor, and then this L filter to smoothen the current ripple. And here we are going to get a very good DC. You can see here. Okay, and this is the simple PWM inverter. This PWM inverter is a high frequency inverter, means high frequency means this is a PWM inverter. Okay, so that our DC is being converted into AC. You can see the fuse sensor because we are having a LCL filter have designed. Okay, so you can see there is a multiple stages. We say that's why we say that it is a multi-stage inverter. Okay, with a high frequency transform. This is a high frequency transform. This is the topology they have given. Most of the topology which I am presenting with respect here, I kept it from initial days to till date. Okay, you can also understand that. Okay, so this topology, you can see that it is like this is the one stage and this is another stage. There is a three power conditioning stages are there. Okay, so you can see there are off cycles. Excuse me. And then here one thing you should understand that you can synchronize, you like this stage and this stage like asynchronously you can control. Also you can control synchronously also. There is no problem, but it is we have two ways of operation. Okay, so you see that how the positive half cycle is being like this DC is convert, like okay, these two switches are on, then DC will get it, and then when the negative half cycle with respect to this, then what will happen? These two will be on, and here you are getting a positive, right? Here you are going to get a negative. Okay, here you are getting a negative because this switch is connected to the lower, and this through this switch our transformer is connecting at the opposite upper input polarity. Okay. And here you see that it is very much suitable for both. It is not for both grid connection as well as the standalone. It is having isolation feature because you have a frequency transformer. This is only not only stepping up, it is also doing the isolation, right? So okay, and power decoupling is very good. We are having in this because we have designed these components. Here we are having either one of these stages. You can design the passive components with a proper power decoupling. Okay, means you are having very good capability here for the power decoupling. Okay, number of stages are multiple, more than 3, and the dual grounding is not required because you are already having a very good isolation. Okay. Even you don't need to like connect your PV module to the ground because you are having a isolation. Okay, it is not required. When there is no transformer, if means galvanic isolation, then you need to have this dual grounding concept. But all the topologies, as I said, they will not be able to provide you this. Okay, this topology is limited for the medium power rating. Okay, we have sized all the components, and then we see the components capabilities, and then because of this frequency transformer and the current and voltage ratings on this, based upon that we cannot go for high power applications in this topology. Okay, so how many switches are there, diodes are there, you can count, and I counted, and captured in this there is no resonance feature is not there. Okay, and the size is very much big. Okay, these are like at the end anyway I will show you the comparison of all these topologies, which is look at the end. Okay, it is very good, suitable for wide range because you are having even the input is very much low, also you will be able to get your desired AC. Okay, cooling requirement is high because you're having high switching losses as well as the conduction losses in the devices, which we have calculated. Because of that, you found that there's a cooling temperature is more, and then it requires a more cooling. Okay, components. Okay. Yes, we have a both positive and negative half cycle. There is a proper symmetrical operation is there. Because of that, why we see this is that if you are having a symmetrical operation in both the half cycle, then we can say that there is a DC offset currents injection will be quite low compared to a symmetrical operation in both the half cycle. Like some topology, they do this. I will show you that. Okay. Without filter, you will not be able to provide a pure DC, pure AC. That's why we need to have a filter on the AC side. And we have the complexity level. In this case, it is low. We are having multiple stages, a lot of power converters, power reluctance switches. So you have a dedicated stage to control the different provide the different control features. Okay, so that's why we say this. Okay, as I said that you can operate in asynchronous mode or synchronous mode when I come to here. Okay, so these are the features which I have discussed. I kept it here. Okay, so now another way is that you say this is multi-stage high frequency transformer. This is this was published in one of the transactions around 1992 or something. Okay, in the initial days, as I said that these are the things I kept it with respect to here and with respect to the features. Okay, and then you see here what they do. I told you that fixed DC, you can also get a rectified natured DC, and then simply here you see that these are not operating at PWM. Okay, here earlier in previous topology, these are operating at PWM. If you remember it, these devices are operating at PWM. This is the switching pulses of this. This is a zoomed view. In 3 cycles I have taken here. Okay, by zooming these pulses to show that how they when they are on there. Okay. So here we can control these devices so that you will be able to get this kind of a DC. Here, without needing of this bulk DC link, they are able to produce this kind of a DC, and then simply we have this line frequency and what it is not a earlier case, it is a high frequency and what if you remember it in the previous one, but now we are using a line frequency. Means these two are on for only 0 to 10 milliseconds and then 10 milliseconds to 20 milliseconds. These two will be on bus, but these are operating at switching frequency. Okay, so this is the operation that, and since we are having, in this case, we have a rectified DC nature DC link, and it is also provide isolation and less conduction losses. And because we are operating, your previous inverter is replaced with line frequency inverter, so it is only this one is applicable for Lincoln. Okay, so and these are the features, like as I said that from the previous way, I kept it all the features which for this converter. Okay, and then in 1994 somewhere they have proposed a pseudo DC link. Okay, without any DC link here. In earlier case we have a DC link. So without that, with the proper control, they increase the burden on the controller to, with the help of the sizing of these devices, okay, these inductors and capacitors, okay, they try to control the DC link and then they try to get this kind of a current they're able to draw and they're able to produce this kind of a voltages with the proper decoupling concept they have applied here. With the help of these, compared to the previous case, this sizing of this inductors and capacitors somewhat crucial, critical. Okay, but they try to avoid the DC link here. Without that, also they are able to get a very good required AC. That is what they claimed when they proposed this inverter. Okay, as I said that with the color coding, you can understand the operation. Okay, so comparing with previous two topologies. Okay, so there is a no link DC link in this. High frequency DC to high frequency and rectified DC after that and DC. Okay, so less cost and the size and volume compared to the previous two topology which I discussed. Okay, so similarly here we can see that the number of components. Okay, and then what they try to do is that another researchers they came and here in the reference number 26, okay, Weberstein and others they have proposed bidirectional DC to high frequency AC and then AC. Okay, so you can see that this with the help of this intent high frequency inverter. Of noise is coming. Okay, yeah. So, all right. Okay, so here you can see that with the help of this high frequency inverter. Okay, so we are able to get here high frequency AC. This high frequency AC we are able to stepping up to a very high frequency AC, and that we are converting into low frequency AC. Okay, this is like AC to AC. Here you can see that this is a one pair of reverse voltage blocking capability devices are required. These two is a reverse voltage blocking capability of devices. Right, you need to block both positive as well as the negative voltages. And also you need to carry the currents in both the directions, right? And so we need to have this kind of arrangement here. Okay, so I kept the color coding. You can see that with the help of that you will be able to understand which are like operating same time. Okay, so you can see the switching, all the switches they are operating at very high frequency. Okay, so this is the equivalent the circuit diagrams, and anyway like the compared to the previous, we can easily understand that there we have AC to DC and then DC to here after this high frequency AC we have a DC and then we have AC, but here we have utilized the concept of PC to AC converters, right? They have utilized it and they proposed and they claimed that here compared to the previous stages, here the one stage got reduced called AC to high frequency to DC and DC to AC. That stage is eliminated. They have claimed that, but this topology, the main drawback, this is not so popular compared to the previous topologies. Although we are using less stages, when you are going for high conversion ratios, like you wanted to, let us take, you wanted to go for 50 kilohertz to 50 hertz, means you need to almost 1,000 times you need to change the frequency. When you go for this much very high, you will lose lot of power quality. So in that case, if you wanted to get a power, very good quality of the power, then you need to have a very big inductor and capacitor to smoothen the voltage and current. That is a very much drawback. And because of this, we will not be able to go for very high frequencies like previous topologies. Here we have a limited range of the frequencies we can go, because if you are going very high times of a frequency conversion, then you will lose the power quality drastically. So that's what we don't want to lose the power quality. By keeping that in mind, you will not be able to go for very high frequencies like the previous case. That is the limitation of this. When we design, we can understand this. Okay, so these are the, here it is only 2 stages. Earlier it is like 3 stages, but here we are having 2 stages. Okay, so and these are the features of this topology like previous, and then so far we have relied on like high frequency based some converter. And in the references like 28, and at the end I have references I will show you. These all topology which I am taking for PV taken from either patents or from reputed journals. Okay. Okay. So when they have proposed and they control for the PV. Okay, the when in case of especially when you say the PV, we need to take care about this MPPT point, right? I hope you are much aware about the MPPT. There is various MPPT techniques are there which should be used to provide this algorithm to control this switch, or you can also provide this. The fundamental concept, if you see that how we can achieve the MPPT, you see that the solar PV characteristics will be like this. Okay, so let us take voltage versus current. Let me say that. Okay. This is a PV curve. Let us take. Okay, this is the maximum power. It is subjected to our load. We are having directly a PV module. Okay. So if you put your load directly to the PV module, this will not be able to provide the maximum power which is it is capable of. Okay, depending upon our load, if you put this load, you will be able to draw this much current. If you put this load, you will be able to draw this much power. If you are able to put this much load, you will be able to see this subject to the load. You will be your power delivered by this PV panel is getting changed. That is a one side. And another side also, if you are depending upon the radiation and temperature, characteristics are getting changed. Okay. So as you see that when the radiation is changed or temperature is changed, then again the power delivered by the panels also getting changed. Okay, so means maximum power is changed, or at the load power is also getting changed. So we need to take care. Some device must be there. Then that should be taking care of this MPPT operation. Whatever load you put, whatever temperature or radiation in my PV module input is like this output to power means voltage and current is depending upon two parameters called temperature and radiation, right? So because your photon current is, if you see that equivalent circuit of your PV module, okay, so it will be something like this. Okay, this is the photon current, and then we have a diode over here, and then we have a shunt resistance and then series resistance. Okay, so this is like a single diode module. Like that we have a two diode module and PV module modeling, and three diode. Like that we have different modeling techniques are there for the PV, because in the like these PV modules are very physical, but you will not, like for our simulation purpose or for our modeling purpose, we need to develop electrical equivalent circuit for these PV modules, okay, which is a function of temperature and radiation. Okay, whatever voltage and current we are getting here, that should match with your physical PV module voltage and current. Then only we can say that this is electrical equivalent of your PV module. Okay, so like as like we have model transformers, or you have model induction machines and all like that, we researchers they found the electrical equivalent circuit for the PV module. You see that this photon current is like I photon is equal to Is into G by G naught into 1 plus alpha delta T. From this you can understand that your photon current is a function of G. G is a irradiation, T is a temperature. When temperature irradiation getting changed, your photon current is changed. When photon current is changed, your PV current will change. Okay, like that means PV current and voltage may change with respect to temperature radiation. So, and also, if load is changed, we have seen that the maximum power delivered to the load is also getting changed. That's why when you say that solar PV system, you need to have some kind of a device, power conditioning unit, subunit that is taking care about this MPPT. Whatever temperature you may have, whatever radiation you may have, whatever load you may have, your this power conditioning unit component should extract all the time the maximum power available from the PV module. That is the role of this MPPT. Okay, so like if you're having two stages, typically in this case we are taking care about this MPPT with this. What it will do, if you see the fundamental concept, okay, so what happens is that, okay, let me take another blank slide and then let me explain. One of the requirement of your PCU is, okay, okay, so if you see that what happens is that you need to extract the maximum power all the time. Okay, whatever temperature you may have, whatever radiation you may have. Okay, so our PCU requirement, one of the requirement is MPPT. How it is tracking MPPT is that you typically, let us say we have used a boost converter. Okay, so okay, so if you used like the in this topology, let me explain this topology in MPPT, and we have used this. What happens is that when the switch on and off is decided by the duty ratio, this duty ratio is telling by your MPPT. MPPT algorithm will decide this much duty ratio must be there to extract the maximum power, okay, from the PV module and based upon your available load. Okay, so let me derive the stuff. Okay, so here we have a VPV and we have here IPV. Okay, so when the switch is on, if you see that the inductor, when the switch is on, what will happen? When the switch is on, this inductor is getting a power. Okay, so inductor is getting charged, and when the switch is on, this diode is forced to be off, and typically we have this capacitor here. This capacitor is pumping power to the load. Okay, so in another case, what will happen based upon your available MPP algorithm duty ratio, it will go to, let us take off state, and then what happens? This switch will goes down, and this PV and inductor together is, when switch is off, this inductor, what is the property inductor, doesn't allow sudden change the current. Previously it got some kind of a current, and it is charged to some current, and that is forcing this diode to on, and then inductor and PV is together is pumping power to the load. Okay, so if you see that in both on and off states, you can see that your inductor voltage is in first case is VL is equal to VPV, and in off case, in the second state, your inductor is nothing but V PV minus V naught. Okay, if the property of inductor is nothing but what it the average voltage across the inductor is 0. If you take into the account, on time means dt and off time is nothing but 1 minus dt. Trying to find out the average voltage, that is nothing but VPV into dt plus of time into 1 minus d into t. That time voltage is VPV minus V naught is equal to this VL average. Okay, so VL average, the property of inductor is nothing but 0, so you will get this. So you see this T and T is there on both, then I'm sending that side. Then you will left with VPV into D plus 1 minus D into VPV minus V naught is equal to 0. So what you will get is that VPV into D, VPV, if I take common, D plus 1 minus D, that is nothing but VPV. VPV minus V naught into 1 minus D you will get, okay, is equal to 0. So we will get V naught is equal to VPV upon 1 minus D, okay. So this is a V naught. Similarly, if you find that I naught, okay, so I naught, what you will get is that you know that this power balancing equation, okay. So from the power balancing equation, we will V naught into I naught is equal to VPV into IPV. Okay, so from this you can say that I naught by IPV is equal to VPV by V naught. Okay, that is nothing but what is VPV by V naught? VPV by V naught is equal to 1 minus D. All right, so that is nothing but you will get I naught is equal to 1 minus D times of IPV. Okay, so what I'm trying to do is that I'm trying to find out my input impedance RPV. Okay, so RPV is nothing but what? Is nothing but VPV upon IPV. Okay, so what is VPV? 1 minus D times of V naught, and what is IPV? IPV is nothing but I naught by 1 minus D. So this is nothing but 1 minus D whole square V naught by I naught. V naught by I naught is nothing but our load resistance. So 1 minus D whole square into our load resistance. This is your PV resistance. Okay. So what happens is that now you can see that. Okay, so if you're having a PV module, just you put a resistance, then what will happen? According to maximum power transfer theorem, your your PV module is having a source resistance, and this is the load. These two should be equal, then only will be able to access the maximum power. Okay, but user may wanted to change the load resistance, whatever temporary radiation may be there, then this will not be, you will not be able to match because your RS is fixed at a certain temporary radiation, but you wanted to change the RL, then this RS is equal RS, RL condition is not satisfying, so we will not be able to get the maximum. That is a mathematical justification. Like earlier, we have seen a graphical justification. But you see that if you have some device, okay, in between these two, okay, so in between these two, I put this converter, okay. So what happens is that even you change RL, okay, you need to map the impedance here that should match with your RS. Okay, so that RP, even you RPV this resistance I said, like input impedance, that must be equal to your RS, right? So these should be equal to RS. That means that even you change RL, okay, so I will be able to, this R not load resistance, I will be able to manage my duty ratio such a way that this entire thing is equal to my source resistance. Means I am controlling duty ratio such a way that, okay, if I decrease R naught, what I will do, I will if I decrease the duty ratio, 1 minus d things will increase, and 1 minus d whole square will increase, then the product remains same, and that matches with RS. Okay, like this, if you wanted to, if you have, even you change the load resistance, okay, your power conditioning is unit is taking care by controlling this duty ratio, and that matches your source resistance and the input impedance offered by your converter. Okay, so like this, you will be able to meet the maximum power point tracking. Okay, that is typically it is possible by controlling the duty ratio. What we do, there is a different MPPT algorithms are imposed in power conditioning unit. Okay, so called incremental conductance or hill climbing technique or PNO technique, and constant voltage technique, constant current, or fractional open circuit, a fractional short circuit current technique. These are the classical MPPT technique. Like that, there is other techniques are there that is responsible to track the maximum power. The fundamental logic is like this: by changing the duty ratio, even you vary the load resistance, you will be able to match your input impedance offered by this entire power conditioning unit to the PV, so that you will be able to extract the maximum. Okay, so like this you will be able to do it. Okay. That is the role. Typically, we do that kind of a thing here in this front-end converter. Okay, that is typical. How will you do is that let us take perturb and observe if you have an idea. So we'll take some initial duty ratio, and then we will inject some perturbation in the duty ratio, and we will find out power in the previous instant and the current instant. Let us take P of k minus 1 and P of k, and the difference is equal or not, we will check. Okay, in this, at this case, if the difference is not equal, then still we will again do perturbation in duty ratio like this. You see that continuously we will change till this point. Once you reach this point, the change in the power is 0 here. Okay, between two consecutive points, the change in the power is 0. That means that our converter will understand we have reached maximum power, and we will not change the duty ratio. Okay, so that is that D at which we are tracking the maximum power. Like this, we will do in case of a PNO technique. Okay. Anyway, I have so like I have all these different MPP technique simulations like this. We have a note also. If time permits, and then within 1.5 hours, I just wanted to show you several topologies, and then if possible, we'll see with the help of simulations. So all the MPP techniques are there. All the 44 topologies of power conditioning units I made. Also, we have the simulations of them, and with the help of them only, I am able to extract the features and then able to compare it, various features of these oral converters. Okay, so. And this here in this topology, like it is suitable for both standalone as well as the grade, and also here it doesn't have any isolation. And also you see that isolation is not there, then one of the requirement is dual current, but still it is also not able to provide it. Okay. So I mean, in some countries, it is very difficult. If you wanted to go for more than 100 volt system, then you need to have very good kind of a features, that is especially in terms of this DC offset injection, and some safety standards we need to fulfill. In other ways, we need to take care to meet the requirement. Like countries like India, we don't see that much about these safety standards generally. Like, but some countries, they do very strictly. They will impose, and they if you are not fulfilling their requirement, then your product will not be able to release into the market. Okay, so that we need to take care when you are not having these two. Right, so we need to have very good control such a way that will not inject any offset current or something like that, and also all other features we should be able to fulfill as per the standards. Okay, number of steps here it is a 2, and okay, see that it is not very suitable for a very wide range. It is only moderated. Coolant requirement is quite like still it is more. Okay, if we are using a silicon devices. Okay, symmetrical operation is there, and without AC side filter, it doesn't will be able to get the required AC. And here control complexity is little bit less because you're having one dedicated converters where you are using your control strategies to get your desired control features. Okay, and then this topology has been proposed by the Saha and Sundar Singh in the IEEE transaction. Okay, they have done the two-stage isolated, non-isolated buck boost inverter-based power conditioning. They have developed for the PV application. Okay, so what they have done is that it is like two switched buck boost converter they have there, and then inverter. We have like the topology they are given, and then it is having we can control these switches in different way. Okay, so to get either you can step up, also you can step down the voltages. That is possible with this kind of a structure. Okay, I highlighted in this oval shape. Okay, so what you do, we can control these switch and this switch synchronously and asynchronously also. Okay, that is quite possible. Okay, so you independent control of this switch is also possible to get your either stepping up the voltage or also stepping down the voltage is also possible. Okay. In previous topology, there is only stepping up feature, is there, stepping down feature is not there. Okay. As I said, you can see that different pulses and input and output voltages. And here, what they have done here, they are controlling these switches such a way that you are having a rectified nature DC link and the current, and then you're able to get this kind of a voltages here. Okay, synchronization is not required, and how they are inductor is getting charged and inductor is discharging, and then inverter positive half cycle and negative half cycle, the equivalent circuits also are captured here. Okay, every figure is very much self-explanatory. That's why I didn't not going in much deep how positive of cycle, negative of cycle is happening. What is the how voltage is stepping up or stepping down. Our inversion is there because we have a limited time. I wanted to cover more topologies. At least I wanted to introduce what are the advancements are there in this power conditioning unit. So that's why. I'm not going much in deep and detailed operation of the each topology. Okay, so and we have simulated all these topologies, and then from that I kept the shape of different voltage and PWM signals so that you can easily understand with the help of those results and the color coding. It is very much easy to understand the topologies. Okay, that is how I presented this. I made this presentation. Okay, so as I said that this is like you see that in the paper itself they have accepted they have designed only for the grid connected with the input only up to 100 due to the safety reasons. As I said that in case of solar, like we need to follow these safety standards also, right? So when we are going for this more than 100 volts, we need to have dual grounding concept. Okay, this is not supporting the dual grounding, so that's why they have limited to only 100 volts. Okay, so if you're going for 100, either you should have proper isolation or you should have a proper dual grounding. You can have a PV system. Okay, so it is like earlier topology, it is also very simple in structure, but compared to the previous two-stage topology, it utilizes a more number of components. And also switching structures are more because you are having this kind of currents on the this inductor and then the switches, they are having more current stresses. Okay, so okay, and line frequency inverter is we are using on the right hand side. That's why I will also switching loss. Okay, and then like previous topologies, we have these all kept it like from the quantified values. Less than 500, less than 1000 watts, okay, 500, 0 to 500, we treated as a low, and then 500 to 3 kilowatt, consider medium, then higher. That classification we have done, and then based upon the switching losses, we have segregated, and then accordingly we have kept this cooling requirement based upon the temperature rise because of the losses and all, right? So, okay, so these are the various features from this topology, and like that, okay, the next one is that in the reference 34, they have proposed based upon this isolated DC-DC converter called flyback. Okay, but boost converter they have developed, and then they have used an inverter. Okay, so here again they are controlling the switch such a way that you will be able to produce this kind of a. Since it is a isolated, this is a mistake, and so you have this kind of isolation is there. So the galvanic isolation is there. So you not be have dual grounding concept is not required as such, and also this is operating at high frequency, and these switches are operating at low frequency, and you can see that. With the help of the magnetizing inductance of this transformer, you will be able to store the energy during the on time of the switch, and then we are trying to release the energy stored in this magnetizing inductance of this transformer, and then we are pumping to this side, and based upon this, we will be having this buck boost nature, right? So it is a buck boost, means it can step up or step down the DC link, and then while you are doing it, you are controlling the switches such a way that you will be able to get the rectified natured DC. Okay, so and then what we are doing is that and this topology is very much limited to the power rating. This is having some kind of restrictions in the power because of these structure which we are having. Okay. So by taking the switching structures and then the transformer capabilities, this topology is limited for the medium low power applications. Okay, cannot get use this topology for very high power. Okay, that is even this was proposed, and their equivalent circuits are equivalent states are connected here, and these are the features of this topology. Since we are running out of the time, just I'm moving very fastly with other topologies. Okay, so since we are left with 8 minutes more, so just and then they have proposed by Fanabiki one topology called. This is also having a buck boost nature, but because of this intermediate capacitor, right, they have added, you can see that to extend the input DC voltage range without any high frequency transformer, the capacitor, intermediate capacitor is added. Okay, so it is acting like a buffer. Okay, is added in the charging loop, so that in these two in together they are providing a voltage, and then we'll be able to step up the voltage, and then you will be able to innovate it. Okay, this kind of a topology needs reverse voltage blocking capable devices. Okay, so. So that is the thing in this topology, you will be able to compared to the previous topologies of this two stages, we can go for higher voltage rating. That's where you can see that how they have controlled the switches, they have kept the switch pulses, and also the different nature of the here the inductor current and then the output voltage. Okay, so. Okay, so great. So how here we are having the intermediate capacitor is helping you to aid the go for the higher voltages. Okay, so by charging, when what happens is that we are going to have this entire voltage. Okay, that is available. Will be available at this link. Okay, so this is how these inductors and capacitors are getting charged and discharged. Various modes we are having. The recurrent circuits I kept it. This topology, as I said, that this topology needs this kind of reverse voltage blocking capability devices. We need to have. Okay.
Hello, sir. Sir, sorry
Yeah.
to interrupt, sir.
Yeah.
Yeah, sir. Actually, the next session will be at 7:30, sir.
Mm-hmm.
So it's a kind request from our side to, if possible, please close the session by 7:30, sir.
Sure. Okay.
Followed with the
So,
questions, sir.
okay, so like this, just okay, okay. Thank you for reminding.
Thank you,
So
sir.
like
Thank you
this,
so
there
much.
is okay. Thank you. Yeah, like these various topology. This topology is proposed in by this Shimizu and Kaiser with active power decoupling. Here I kept it like. Which is responsible for bucking and boosting this green color in this pattern. Okay, that is responsible for buck boost, and this is responsible for black. Here I've used the color notation that is for flyback and buck boost features that clearly are segregated with this the help of this color coding. And then the pulses here, you see that this switch is only on for on time, and this switch is on during negative off cycle of your AC side. Okay, like this they control the switches, and we are able to get both buck and buck boost principle as well as the flyback operation they are able to achieve. And with the help of this flyback nature, what they are trying to do is that they are offering decoupling. Okay, they try to use this capacitor with the flyback concept. They are able to provide a good decoupling, and with the help of this buck boost nature, we are able to get the boosting other two features required in power conditioning. Okay, and then okay, all the features kept, and then the next paper they have proposed with enhanced power decoupling. Okay, there is added with more power semiconductor devices, like it's the same like I kept a green and this black to flyback as well as the buck boost nature. Okay. Okay, like this, there are various topologies are there. Since now the time is where is about over. So with this, like I wanted to tell you that like this, there is a lot of topologies are there. Okay, so with some resonant based, and then some are like flyback type directly inverter. Okay, and then some are like single stage series resonant solar PV inverter. Like that, various topologies I have reviewed, and then we have simulated. You can see that simulation result and their equivalent circuit with the help of color coding and mining. Finally, okay, like this, I have almost 44 topologies. We have done it in this presentation. Okay. Okay, so with this is a H5 topology proposed by SME H5 H6. Eric is also there. Okay, and then at the end, I have compared all these topologies with respect to their different features. Okay, you can see that. Okay, and then once we have done that, we can see that some are like very good for single stage and centralized single stage, and some are good for PCU. Two-stage PCUs are good for AC modules, and they are able to provide a voltage amplification. If several strings are connected to the grid, multi-string concept is very good, and that like that. Actually, if you are interested, I will I will share you all the features of this topology. I have more detailed comparisons and their power rating, losses, everything. I will share with the organizers. Okay, so if someone is interested or they want to do some kind of research in this area, we can go through it. Okay, like with this, I wanted to stop my discussion, and if you have any queries, you feel free to yeah, discuss.
Thank you, sir. Thank you very much. Dear participants, if you have any questions, please ask to sir. If anyone is having any query, please. Even you can post your question in the chat box also. Sir, I have a question, sir, regarding with the research. Sir, am I audible, sir?
Sir, our voice is not clear, sir.
Yeah, okay, sir. Now it is audible, sir?
Sir, your voice is audible, but with lot of echo is coming actually.
Echo. Sir. Mic speaker. Sir, now it is audible, sir?
Yeah, fine, sir. Fine. Yeah. Tell me.
Sir, could you please suggest, what are the main research gaps in the AC, what do you call AC converter frequency link design, sir? So that
Sorry, sir.
we can explore. Sir, the
Hello.
main research gaps. Hello, sir. Yes, sir.
Sir, actually echo is coming, sir. I couldn't understand actually what you're.
Muted. Sir. Now please check, sir. Is it audible, sir?
But fine, sir. But the echo is there, but it is bit fine here, better than previous. What you are saying, sir?
Hello, sir.
Yeah. Please tell, sir.
Hello.
Yes, sir. Yes.
Yes, sir. Yeah, okay, sir. Sir, just wanted asking about the main research gaps, sir, for high frequency AC link design, sir. What are the major research gaps so that we can explore more in that particular area, sir?
Yes, sir. Yes. Okay. So I think you are asking about high frequency inverters research gaps in that area, right, sir?
Yes, sir.
Okay. Yes, sir. Actually, yeah, there is a various topologies have been emerged in this case of solar PV applications. There is H5 topology, H6 topology. They are very good in terms of reliability. If people are working on the reliability, we can find as even in the previous session we have discussed about requirements of the PV. Like our main focus is that efficiency and reliability. Okay, we should be able to provide a very good life to the customers, and also when we are talking about the solar PV, while achieving all the control features and also all these requirements with the proper control strategies we need to have. And also the adoption of wideband gap devices while we are operating at very high switching frequencies, they are imposing some kind of a challenges due to this common. Just all these things we can address.
Okay, sir. Sure, sir. Thank you so much, sir. Sir, there is a question in the chat box, sir. So, which filter design will be preferred to eliminate DC ripple in converter design? So, this
Generally, like in case of a PV, generally the DC link C filter itself is sufficient to eliminate the DC ripple. If you are talking about the CMI and all, there is some kind of a small common mode chokes, and then there is a C filter is required to eliminate the ripples on the input side DC cell.
Okay, sir. Okay, sir. Thank you, sir. So, dear participants, if you have any questions, please interact. So if we don't have any questions, then we'll be closing the session. So thank you very much, Dr. Ravindra sir, for another insightful and technical detailed session. So your demonstration of simulation-based analysis and converter integration for EVs has truly deepened our understanding of solar-fed electric mobility systems. So we, on behalf of Vishnu Institute of Technology, Bhimavaram, and from the organizing team, as well as on behalf of the participants, we pay a heartfelt thanks to you, sir, for accepting our invitation and being a part of this ATL FDP. Thank you very much, sir.
Yeah, thank you very much, sir. Thank you very much for giving me this opportunity to present some of my work here, and thank you very much for wonderful organizing this FDP in wonderful way. And thank you very much, Kasireddy sir, for inviting me for this FDP. And thank you very much for all the participants who are spending your valuable time to attend this FDP. Thank you very much. Thank you, sir. Can I leave, sir?
Yes, sir. Yes, sir. Yes, sir. Thank you.
Thank you, sir.
Thank you. Good day, sir. Okay, thanks. Bye.
Hello. Yeah, Kasi
Sir,
sir.
sir.
Are you able to
Sir,
hear my voice?
Yes, sir, sir. You are audible, sir.
Yeah.
Sir, we'll be making you presenter, sir.
Yeah. Very good evening, one and all.
Sir,
Yeah.
sir, good evening, sir. Sir, okay, sir. Can we take a short break of 2 to 3 minutes, sir?
Sure.
Then
No
we'll
problem.
be rejoining, sir. Dear
Sure.
participants, please take a short break of 2 to 3 minutes. Then again, please stay connected and we'll be rejoining the session. Thank you. So welcome back again. Sir, with your permission, can we start, sir?
Yes, sir. Please.
Thank you, sir. So, dear participants, we now move to our next session for the evening by Shri K. Satish Kumar, sir, Deputy Director, Central Electricity Authority, CEA, New Delhi, who brings extensive expertise in grid monitoring, system protection, and renewable integration frameworks. I request Dr. I. Kasireddy to introduce our today's resource person. Over to you, sir.
So thank you, Dr. Reddy Kasim. So Sri K. Satish Kumar completed his post-graduation in power systems from NIT Warangal, graduating as topper of the EEE department. He was honored with the POSACO Power System Award from IIT Delhi for having the best MTech project in India. During his MTech, he published various research papers in reputed journals such as IEEE and elsewhere. He successfully cleared multiple competitive examinations, including those conducted by BARC, ECIL, Power Grid Corporation of India, and various state GENCOs and DISCOMs, securing positions as an assistant engineer. In 2016, he qualified for the UPSC Engineering Service and joined the Central Electricity Authority as an assistant director. In this role, he has played a key part in sanctioning more than 100 projects worth over 5,000 crore under the Power System Development Fund. So thank you very much, sir, for being here.
So thank you, Dr. Kasireddy, for a nice introduction. So dear participants, please join me in warm welcoming Sri K. Satish Kumar Garu to share his expertise with us. So over to you, sir.
You are muted, sir.
Sir, you
Please
are
unmute.
muted, sir. Please.
Yeah. Thank you, sir, for giving me this opportunity to present this technical topic. Now I'm sharing because the time is running up. So now we'll start with the technical presentation on this. So role of PMU in real-time power system operation and control. This is a brief contents which we are going to discuss now. SCADA versus VAMS, nothing but PMU, wide area measurement system. We'll compare with the older system, which is SCADA, supervisory control and data acquisition system. And just before going through the applications, we'll discuss about the brief introduction about the PMU, working principle of PMU, and what are the stages in the development of PMU. And we'll see one sample qualitrial company PMU datasheet to understand exactly what data it takes and what data it gives. And next, we'll discuss on PMU vendors in India. Then we'll go through the initial phase in India, the synchro phases initial pilot project in India. And then we'll understand mathematical equation, which will basically helps in how exactly PME works and what are the mathematical equations associated with. And after this brief introduction, we'll go through the applications. What are the real-time applications? We'll go through some case studies, real-time case studies, and then we'll discuss what is the present status of the these projects and what is the present status of this phasor measurement units in India. And then we'll go through some challenges and suggestions. So now if we go through the older version, which is SCADA, many of you know that this supervisory control and data acquisition system having some problems. It is very slow system. For example, now we'll compare with these futures with this SCADA and VAMS. This data periodicity, that SCADA system reports every 4 to 10 seconds, whereas this PMU present technology, which every 10 milliseconds it will sense the data from the power system to from substations to these control centers. So you can see around 1,000-fold the accuracy of data and the speed of data you'll get from this PMUs compared to your SCADA. if you use this SCADA system every 4 seconds to 5 seconds, the data will be updated. But in the PMU latest, this WAMS system or WAMS technology, every 10 milliseconds, the data will be reported to control center. You will get very much accurate data compared to your SCADA system. Now, angle measurement. In olden system like SCADA system, it is not possible to measure the angle, because to measure the angle, both substation, you should capture the data at the both substations at the same time. And this SCADA system, as this is not a synchronized system while capturing the data. So for example, you are capturing data at one time at one substation, 7:30 you're capturing at one substation, and 7 hours 30 minutes and 2 seconds you're capturing the other substation. So you cannot compare this data, and accordingly you cannot measure the angle between these two substation, phase angle between these two substations, because these two are captured at slightly different time. So within this difference of milliseconds, as you know, power system is a very dynamic system. Within this millisecond, the parameters will change, so it is not possible for you to measure the this angle measurement in the SCADA. Whereas you can the PMU, now I will tell in the next slides how we will exactly measure the phase angle, which is not possible in SCADA, whether it is how it is possible in PMU technology. In PMU, you will use GPS as a reference. So exactly at the same time, you will measure using GPS as your reference. It will give the signals to all PMUs at the same time. So all PMUs will measure at the same seconds, milliseconds, and microseconds. So you can compare the phase angle between one substation to other. So from Kashmir to Kanyakumari, from Gujarat to Assam, you can measure the phase angle between the any substations. And oscillation monitoring, as I told, these oscillations are of low frequency or high frequency. Then to measure or to see these oscillations, you need high speed data from the substations to the control center. You need very much accurate data, which is not possible in the SCADA system. That's why we are using PMU system now. So in this PMU system, in this WAM system, you can see the oscillations. And next, post fault analysis, because you have the huge real data, you have very much accurate data with milliseconds and microsecond. You can do post fault analysis from this PMU data. Now you can see, as I told, this you can see this SCADA system and WAM system. In the first PMU bus voltage, you can see the accuracy level, which is in range of milliseconds, and you can see the phase PMU phase currents in the range of milli and microseconds. Whereas in the SCADA bus voltage, if you see in the downside, this it is in the range of seconds. So you cannot know, even for example, in a fault takes place, you cannot tell exactly where the location of fault and how the voltages are responded in the microseconds and the millisecond, how voltages is changed from within the milliseconds and microseconds, because the SCADA system itself gives the updated voltages every 4 seconds, every 5 seconds. So within this 4 seconds is enough that fault can be cleared or fault can be created. So within this time, you will miss the as you don't have much accurate data in the SCADA system. So it is really difficult to understand exactly where is the location of the fault and whether that fault is cleared or not. It is really difficult to understand from the SCADA data. So now before that, we'll see what is exactly PMU. I am telling about this all PMU advantages of PMU. You have very much accurate data. You can measure the angle and you can see the oscillations. You have many hundreds of applications. You have hundreds of benefits from using this PMU. But before that, we'll understand what is PMU. So PMU is a phasor measurement unit. It's a device. PMU is a phasor measurement unit, or synchrophizer is a device which measures the electrical waves on the electric grid using common time source for synchronization. So here the common time source, GPS, for synchronization is the key word which will helps the data. You have common data, means you have a common frame for comparing the data in the power system. So in the SCADA system, you don't have any synchronization between the data, but in the PMU system or WAM system, you have a synchronized data. So you can compare any data by having same common time. So, and this is the working principle of PMU, how exactly a PMU works in a substation. For example, you are placed a PMU in the substation. What are the inputs to this PMU? Three-phase voltages and three-phase currents are the inputs to PMU. You will give this three-phase voltages and currents to the PMU, and you will get output in the modem. In the output of this microprocessor is the phasors, positive sequence components of the voltage currents. You will get the positive sequence of components of the voltage and currents. From that, you can calculate anything else. Here we'll give three-phase voltages and currents to this anti-aliasing filter, which is it's a anti-aliasing filter is nothing but it's a low-pass filter. It eliminates any high-frequency disturbances or in the signals. It will eliminate this this. It removes that, and after that, this it will gives to a 16-bit or the 32-bit AD converter, which will convert this analog signal to digital signals, and this digital signal given to microprocessor. And this microprocessor uses some Fourier transforms, which will accordingly it will calculate the phasors from the analog signals. Here, the GPS receiver will help to synchronize all PMUs in the power system, and this GPS signal is gives to phasor lock oscillators. In case of GPS receiver, for example, GPS receiver will not be available due to some reason for 1-2 seconds. In this duration, this phasor lock oscillator will be already in lock with GPS signal, so it will continue with that locking, so it will not get any impact on the GPS. For example, if it is not available for 1 second, it will not have any problem because it is already phase locked. So once GPS signals comes, then it is one continuously it will links with this it locks with the phasor lock oscillator, and this gives the converter. Accordingly, once this microprocessor process the data, unlock data, digital data, and it gives the processed phasors, which is three-phase voltages and three-phase currents, and this data will be transformed to PDC. PDC is nothing but it is like server. It will be placed at control centers of state load dispatch center, regional load dispatch center, or national load dispatch centers, and this data will be the data from the PMU is transferred to the PDC. PDC nothing but servers. Now it is in simple map. I can show this PMU. This current transformer. You are giving inputs from current transformer, and you are giving the voltage. You are giving three-phase currents RYB as the inputs, and you are giving the voltages RYB as the inputs. Here currents nothing but it not in hundreds of thousands. You are using the CT. From the CT, you are giving this 1 amp or 1 amp and 2 amps that reading. Similarly, here voltage also you will use the PTs. You will take the measurement PTs inputs from the measurement PTs, and you will give that inputs to this PMU here. So you can see this PMU having inputs of current and voltages and GPS, and the output of this PMU is current and voltage phasors. And using this current and voltage phasors, you can automatically it will calculates, that processor calculates real and reactive powers and phasor differences, and also it gives the other signals. Now, what is the synchronizing sampling exactly? So, for example, there are two substations, substation A and substation B. They are different location, like 100 kilometers or 200 kilometers. So you need a common reference for measuring this data. If you measured at the same time, then only you can compare these two voltages, and you can tell what is the angle difference between substation A and substation B. So this synchronized clock pulses, which we discussed earlier, the synchronized pulses are used for sampling voltages and current of these three phases at the two substation, and adds time tag. So whatever the PMU measures, it will measure the data and also adds time tag. So each measurement will be having some stamp of time tag. So for example, now the time is 7:53. So PMU is measuring voltage and current here. So it will measure the data, what is the amplitude and what is the angle, and also it will stamp the data with 7 hours 54 minutes 30 seconds, and 20 milliseconds. So it will stamp every data. So you have the data which is stamped. You can compare all the common time frames to get the accurate data. So here it is, as I told, there are many PMs in the power system. So each PM is synchronized with GPS, and GPS will be acts like a reference. Once PMO takes the samples, the data, and it will PMO processor gives the output of phasors, and these phasors or output will be transferred to PDC. PDC is nothing but a servers which are located at the state load dispatch center, and regional load dispatch center, and national load dispatch center. So now just a brief introduction about the PMO when it is developed. There is a blackout in 1965 in Northeast United States, which leads to the research in power system operation to make the power system more secure. So there are US Energy Department funded huge funds for this development of the device. Accordingly, finally in 1988, Dr. Arun G. Padkhe and James, they developed a prototype PMU in 1965. So before in the development of this PMU, there are different stages. In the first, they developed the symmetrical component distance relay, and then they added the synchronization process to that, and then they developed a prototype PMU. You can see this is the prototype PMU in 1965. And this I took the photo of actual PMO, which is at NTPC Ramagundam. This is a self-manufactured PMO, which is at NTPC Ramagundam. And this is I took photo in when I went to IIT Kanpur. They have a laboratory, RTDLS, real-time digital simulation something. They have the lab which is they real time they're taking the data from the power system, and they're measuring, and they're using for the research purpose in IIT Kanpur. What are the mathematical equation? Now, as you know, these which are backgroundly they are working in the processor. So as you know, this a sinusoidal signal will represent generally with the x of t is called xm cos omega t plus phi, and here xm by root 2 is the amplitude, and this phi is the angle. So generally, these are discrete inputs. As you know, this continuous waveform is when you get samples, it will get the discrete signals. Discrete when you convert this analog to digital, you will get this discrete in the form. So that will be given to this processor. It will use a discrete Fourier transform to compute these phasors. This is a discrete Fourier transform function which is used inside the processor to get this output of the phasors. Generally, the output are positive sequence, negative sequence, and zero sequence sequence components. And using this positive, negative, zero sequence components, you can calculate anything. Now, what are the types of PMU? Now we are discussing about PMU, but there are two types generally in the PMUs. One is M means measurement type PMU, and another is the P type protection type PMU. In India, we are using M type measurement purpose only. We are not even started this protection PMU. Though recently, National Power Committee meeting suggested for the installation of few protection type PMUs to in the future, like in the maybe in the with the next 5 to 10 years, we'll have a proper pilot project. Based on the results, we may expand this protection type PMUs application. But as of now, we are limited to only measurement PMU. Now we'll see what is the difference between this measurement PMU and protection PMU. In measurement PMU, the objective is measurement. So you will have higher PMU reporting data, but it is little slower. As you know, in the protection, you cannot take more time. So it is should be faster. In protection type PMU, it is comparatively faster, but the data is not that accurate. Whereas in measurement PMU, you will have the higher reporting data, but a little slower. Now in India, there are major PMU vendors are Siemens, Hitachi, Macrodyne, and Qualitrol, Cell, Alstom, which is in the range. The cost of PMU, we approved this project for Power Grid on the UAT DSM phase 1 project. The cost is approximately 4-5 lakhs based on the number of inputs. I will tell this now. We'll see the some PMU data sheet to understand exactly what are the technical specifications of a PMU can be there. Like now, the voltage range is from 88 to 300 volts power supply, and Pmax is 40. QPMU 9 channel. Similarly, you have QPMU Qualitrol company PMU 18 channel and 36 channels. Just I will tell these channels what is these channels. For example, now you are connecting, this is a PMU backside. But these are three-phase CT. You are taking three inputs, and you are taking from PT. You are taking the three inputs, three-phase CT and three-phase VT. So each is taken as a one channel. One channel means three pins. Either you can it's CT or PT. Now here it is a 9 channel or 18 channel or 36. You can understand because it's a multiples of 3. So here 3 PMU 9 means 9 channels. Here 9 channels means you can take 3 voltage 3 RYB of voltage RYB of current. Similarly here 18 channel. Generally bus voltage only they will take one, and remaining are the currents. So here in 9 PMU 9 channel means R phase, Y phase, B phase of voltage, and the remaining 6 are for the two lines. Each line having the RYB. So there are two lines it can measure. Here in 18 channel PMU, one is for bus voltage RYB, and remaining 15 are for uh, currents of five lines. Now here the front panel, they will have LED indicators which it shows whether unit is health or communication is in progress, whether clock is synchronized. So you can see this LED indicators. It tells the status of the PMU. So using these signals you can understand whether communication is working, because by physically you cannot tell that whether communication is going on or clock is synchronized or not. So they given these LED indicators which tells whether the clock is synchronized or not, and whether unit is healthy, whether communication is progress or not. And analog channels, as I told, analog channels means what? Your CTPT inputs. Digital channels means it will tells whether CB is open or not, whether relay is functioning or not. These are the digital channels. 1 and 0 are the digital inputs, whereas analog channels are like your voltage and currents are the analog inputs. Here the accuracy in the range of 1% TV. TV means total vector error, which is for current it is 1% of accuracy. For voltage also it is of total vector error is in the range of 1%. Performance sample rate. As I told, we'll take the samples from the inputs. Here, as I told before, this PMU takes the inputs from three-phase voltages and currents. So you need here the you'll give to anti-aliasing filter after the sampling. Here the sample rate you can see it is in the range of 512 samples per cycle. Each cycle is 20, as we have a 50 Hz power system, each cycle is 20 milliseconds. So now each 20 milliseconds, this PMU takes 512 samples. One sine cycle, you are taking 512 samples. So you can understand the accuracy level and the speed of data it will report to the control centers. Now, accuracy of PMU, which is at the 1 microsecond when it is locked. Communications, it will uses the RJ45 and also next comes to phaser. We'll have C37118, which is IEEE standards. The standards will help the manufacturers to have a common standards so that they can interoperable, and they can maintain the same standards so that they can interconnected, and they can use any PMU, any manufacturer in the system. So while they are integration, while integrating these different manufacturers, we don't have any problem. Here frames rate, it is phasers. It is mentioned that frame rates up to 50 to frame rates up to 50 or 60 hertz. here I will tell this frames a PMU each. For example, I'll tell the PMU is reporting at 50 FPS. FPS means frames per second. It means in each second this PMU report to control center 50 frames. Each frame contains voltage data, current data, frequency data, df by dt. All this data in the each frame, it will have all this data, voltage and current and frequency, df by dt, all this data. So for example, if I say a PMU is reporting at 50 fps, 50 frames per second, it means in each second it's sending 50 frames to the control center. You can understand the accuracy of that data. Now we'll come to the what is the synchro phasors initiate in India. So initially this there now earlier it is called POSOCO, now it is called Power Grid India. Grid they started with this pilot project of 52 PMUs in the country in the from 2008 to 2010, and from the feedback from this pilot project, they prepared the DPR in 2012 and they submitted to Central Electricity Authority, and we approved this project in 2012 for implementation of 1740 PMUs in Pan India. And finally, CRC granted in principle approval for this implementation of URTDSM phase 1, unified real-time this project. In the phase 1 we CRC given this approval, but they told very clearly that for phase 2 you need to take the feedback from the phase 1 from the POSOCO. After the feedback from phase 1, they will be allowed to go for the phase 2. In the phase 1, these are the number of PMUs and PDCs are installed in the these are proposed. Basically this table shows the proposed in the northern region and western region, eastern region, southern region, northeast region. These are the substations and these are the number of transmission lines and these are the PMUs. Here ISTS is interstate transmission transmission system, and the ST is the state transmission unit. And these are the nodal PDCs, main PDCs, SPDs. I will show in the next diagram what is this exactly nodal PDC and PDC. They proposed for around 1740, but in the phase 1 actually you can see here 1186 are the in the stage 1, but because of the some substation, some base are increased, and there is a increase in the actual quantity of PMUs. So finally out of 1186 they commissioned 1409 PMUs in the phase 1. The phase 1 is basically the CRC given permission wherever this fiber optic communication is available, because now you can understand the quantity of data, the speed of data. So you to deal this with the speed of data and the accuracy of data and such a large quantity of data, you need fiber optic communication network. So this phase 1, stage 1 of this phase 1 is implemented wherever already communication is available. So they just installed the PMU, already this fiber optic communication is there at that substations. Using this fiber optic communication, this PMU user to transfer the data to PDC. PDC is nothing but phasor data concentrator, which is nothing but a server which stores the data of PMU. And it will you have some analytics. This analytics takes the data from PDC and it will analyzes the data and it gives the outcomes. As I told, this Power Grid implemented this URTDSM project in 2014. 1409 PMUs are installed in the phase 1. And this nodal PDC at a strategic substation. For example, I have a nearby within 50 kilometers, I have a 10-20 substations. So what I will do generally, I will keep one middle substation as a nodal substation. I will take the data from nearest all PMUs and I will store in the that nodal substation PDC. So that's why it is called nodal PDC strategic substation. Then it will give to data to master PDC, which is there in the SLDCs, and then super PDC. This PDCs are nothing but phasor data. These are nothing but your servers, which are there at RLDC, regional load dispatch centers, and state load dispensers. So PMUs are installed in the phase one, only those 400 kV lines which had a connectivity of fiber, as I told earlier. And then after, because you have a lot of data, you need some analytics. Using this large data, you need analytics. This analytics will help in understanding the data. Otherwise, if you have a raw data of such a huge quantity without any analytics, it is not possible to analyze what exactly you want. Like what you want to see voltage contours, you want to see frequency contours. For that, you need a application. So finally, GE developed in the phase one 6 analytics they developed with the help of IIT Bombay, and they using this application, 6 applications, you can see the exact data. So as I told, these are configuration how exactly this URTDSM phase one works. These are the substations. Some PMUs are located at the state sector substations. Some PMUs are located IPPs, individual this and some PMUs located at central substations. Some PMUs are located at power grid substations. You can see this configuration, how they are transmitting the data to the next level, which is master PDC at strategic locations, or master PDC at master PDC, which are available at the state load dispatch centers. And you can see there is always redundancy. This switch, they will collecting, this LAN switch is collecting 2-3 PMS data, and it is transmitting to one PDC, master PDC at SLDC, and also it is transmitting to the data to the strategic location in the state. And this master PDCs are next they're transferring this data to the super PDCs, which are having at the RLDCs. RLDC is nothing but regional load dispatch center. We have 5 regional load dispatchers in India. One is northern regional load dispatch center, which is there in Delhi. We have southern regional load dispatch center, Bangalore. And you have a western regional load dispatch center at Mumbai. You have a northeastern we'll have in Shillong, and eastern we'll have in Kolkata. So in India we have 5 regional load dispatch centers, and they will transfer this data to super PDC, which is at NLDC, National Load Dispatch Center, which is in Delhi. And there is one more power grid PMS report to directly to NTMC PDC. Here NTMC is National Transmission Asset Management Center, which is there in Manesar in Delhi, Gurgaon. So the data is this data from the super PDC also they interchange, like NLDC data they will send that can be accessed to this NTMC, and NTMC data can be accessed from NLDC. And there is one more backup PDC also there at super PDC, which is I think in ARLDC. They have a backup center in ARLDC. In C also we have 3 remote consoles. In a daily basis, I also go through this data. We'll see in CA, GM division and NPC division having these remote consoles. Remote console nothing but you are having the access to this entire PDC. You can see the data, real-time data, what is in each and every substation. You can just by clicking a button, you can see what is the real-time power, real-time voltage, real-time frequency. You can everything you can see in India map. It is a in Indian geography. You can see the voltages and phasor voltages, frequency, and currents. You can see. Now we'll comes to the applications. The most important part of this PMU is applications. What are the applications? One is real-time applications. Real-time means the control center what we'll use in the real time. With respect to control center, real-time applications and offline applications. What are the real-time applications? You can visualize magnitude and angle of all the 3-phase currents and voltages. And another thing is what all you can visualize is sequence of components of voltages and frequency difference, rate of change of frequency, angular separation between the nodes as I explained earlier, and single phase or auto reclosing EHV transmission line. It is just like taken major things which I need to explain. So there are many things you can visualize, because once you have the voltage, you have the current and phase angle, you can calculate anything from these 3 components. And what are the offline applications? Generally, this forensic analysis of fault grid events. For example, I need to analyze some last month or last week data. You already it is there in the PDC. You can go through the data and you can analyze this. This is the offline applications. There is a one group is there in NLDC and all the RLDCs, that system study group. They always they will go through this past data, and they will go and analyze for the publish of reports and to get some conclusions and do certain simulation studies. They will use the data. So what is offline applications? Detection of grid events within and other regions. Type of fault. Once you have phase sequence measurement, already PMO gives you your positive sequence components of voltages and currents. Using that positive sequence component voltages and currents, you can tell whether it's LG fault, LL fault, LLG fault, triple L fault, triple LG fault. And what is the nature of fault, whether it is a dead short circuit or high resistance. As you know, dead short circuit means the voltage will be almost zero, whereas high resistance fault, the voltage will be there because of the fault resistance. Next, the time of fault and sequence events. In the SCADA, as I told, every 4 seconds the data will be there. So you don't know within milliseconds or microseconds, I can say the fault will be initiated and fault will be spread in the power system. So you don't know from where exactly the fault is started. But in PM, you have such accurate data, and in the range of milliseconds and microseconds, you can easily do postmortem analysis, and you can tell exactly what are the sequence of events and the fault, and you can also locate what is the location fault location, from which substation it is started. You can easily tell because the time is so accurate and also very in the range of microseconds and milliseconds. You can tell easily from where this fault is started. And fault clearance time, probable location of fault, voltage recovery post fault clearance, and possible protection operation, misoperations, single phase auto replacing in EHV transmission also you can observe, because it is in the range of milliseconds and microseconds. You can go through this offline applications. And next other is within this offline applications, post dispatch analysis of grid. As I said, you will use that data for many number of applications. For example, generally common people think if fault is bad for the system, but if you ask the power system operators, they will take the benefit of fault using this data. Like they will validate their models. For example, I'm a system operator. I sat in NLDC. So whether I want to know whether my model is accurate or not, so for that I need a data. So I will take the real-time data in the power system. I will simulate the same fault in the my model. Whether this data I will compare with the real data with my which I prepared my simulator model. I will compare with this data with the real-time fault data, whether it is both are matching or not. So I can I will validate that my model, whether my model is correct and accurate or not. So using this fault data, many are using this previous fault data. They will validate their network models. And you can using this you can also validate this transfer capability declaration, simulated short circuit you can do, and substation disturbance recorder. It act like a substation, whether substation disturbance recorder is working or not properly with the accurate time they are storing the data or not. Also you can compare with PMU data, and you can also compare your substation event log with PMU data, whether that the substation equipments and instruments are working and giving the accurate data or not. You can see. And some applications are taken, and we can also discuss about the computation of system inertia H using day by dt, and frequency response characteristics we'll see. These are all are the benefits and from this PMU. Detection and analysis of oscillations. As I told, this is in the range of millis and microseconds. So you can plot the data and you can see whether any low frequency or high frequency oscillations are there in the power system. So detection of time, duration, amplitude, frequency of the oscillation you can find. and there is type of oscillation, whether inter-area or local oscillations, and nature of the oscillations, like whether it is undamped oscillation or not a damped, not damped, damped oscillation, and modes present, whether their amplitude and damping factor, whether coherent group of generators, whether few generators are uh, you can divide which generators are exactly the coherent group. It means coherent group means for a fault, a few generators mimic same, they will exhibit like same, and few generators they will not exhibit the same. So you can identify what are the coherent group of generators from this data. So these are the some real-time applications. I will show the exactly the PMU images. So these are the PMU images. You can see the accuracy of the data. You can see in the range of milliseconds. Voltage and currents, rate of change of frequency, and frequency plots. So this application is monitoring application. You can visualize the voltages and currents. This is a phase angle. So here Vindhyachal taken as a reference, and from Vindhyachal you can take as a reference. The advantage with PMU is, like in India we have 1400 PMUs. You can take any PMU as a reference, and you can compare the phase angle between the you can take that as a reference. For example, I will take Ramagundam as a reference, and I will compare this Ramagundam voltage with Assam substation voltage. What is the phase angle between these two substations? So you can change the reference also. Accordingly, the plots will come by whichever you prefer the reference. Accordingly, it will take the reference, and it will give the remaining phase angles with respect to that. You can see the voltages of Hisar, Bassi, Vindhyachal, Dadri, Agra, Kanpur, and Moga. There is from zero, this purple color is far away, and then this blue color is very near. So Hisar voltage from this from Vindhyachal is very near, and the angle between is low, not near, I can say. The voltage angle between this phase angle is small, and where compared to others is low. So other many of you know the state estimation. What is the we'll see how PMU helped state estimation. Many of you know this state estimation is a we'll use this state estimation algorithm with the help of load flows only. Initially, because of the raw data, we'll run the load flows, and then we'll comes to the state estimation because we don't have the much accurate data. What is that state exactly? So the complex bus voltages are the state of the system. For example, I want to know if I know the all bus voltages, complex bus voltages, then I can say the that entire system state I can know, because if you know the voltage and with phase angle at every substation, you can calculate current, and using that impedances you can calculate current, and you can calculate voltage, power, you can active power, reactive power, anything you can calculate. So that's why says if you know the complex bus voltage of the each substation, then you can know the state of the system. What is the state, whether it is in which state exactly, whether it is really in emergency mode, like if your phase angles are in the range of 30-40. So using these phase voltages, you can calculate, and you can tell the system state. That's why the state estimation says, my teacher used to say, if you know the bus voltages, that you can tell everything about the system. So the most important is the state, nothing but here the complex bus voltages are the state of the system. This existing state estimation algorithm uses measurements of the line flows and injections, both real reactive powers, at all the bus voltages of angles and magnitude. The problem with the conventional state estimation is we'll run the state estimation with the assumption that this data is a static. As I told, the SCADA system, the problem with SCADA system is will not take the data at the same time from the all the substations. There's measured at different times. So as a system is dynamic, when you're taking the measurements of all the substations at different times, so that the data is not accurate, because you're measuring at different times of the system. You should measure exactly at the same time to know the system state. Here, we'll assume generally in the static assumption, we'll assume in the state estimator that the data is static. It is an assumption because SCADA will not get the static data, we'll get different timing data, but we'll use assumption, we'll use this assumption and we'll run the state estimator till it's a recurrence. We'll use many cycles. It is a iterative process. The state estimation is a iterative process because of the static assumption. We'll do this iterative process. We'll run state estimation till convergence. So that will converge only when the data accurate. When there is a data, there is a data accuracy. So, but the advantage with PMU, as I told, this assumption itself will be removed, right? Static assumption itself will be removed in the PMU, and you will directly get the linear state estimation. So you will not use this basic algorithms. You will run many times. There is no iterative process in PMU because PMU you are directly measuring the state of the system because you have a common resource, common GPS signal. That's a common platform. Using that common GPS, you will directly measure the system. So there is no calculation of the state of the system. You will directly measure. So the difference between state estimation with conventional system and the state estimation with PMUs is you will do all this mathematical equation. You will run the equations iteratively to get the accurate result in the conventional. But whereas in PM, you will directly measure the state of the system. So there is no iterative process. It's a simple linear equation or problem. It will be directly solved. There is no iterative process. So prior to synchronized phasor, the state could not be measured directly, but because of the PMU, now you can measure directly the state of the system. No, this is my MTech project on which placement of PMUs I worked on during my MTech. Now, for state estimation, the first step is you will place the PMUs. Optimal PMU is the first step in the state estimation. Just I will brief I will not go through in depth. Just I will brief. For example, if I place PMU at number 4 node, so I can measure directly the voltage at number 2 at node 2, and I can also measure the at node 3. I can also measure the at node 7 and 9 because if I know the voltage at 4, if I know the voltage at 4, and I also know using PMU, I know the voltage at 4 because I placed the PMU at node number 4, and I also know the currents flowing between this 2 and 4, 3 and 4, and this 4 and 9 because we'll measure the currents in these lines, and you know already the impedance line. Using this voltage and the impedance drop in this line, you can calculate voltage at 2, 3, 7, 5 and 9. So it means the directly connected with 4, which are 2, 3, 5, 7, 9. So it means there is really no need of putting your PMU at node 2, node 3, node 7, node 9 because the PMU, if you are placed at PMU at 4, that will help automatically measurement of voltage at 2, 3, 5, 7, 9. So accordingly, if you choose PMU in proper way to measure this all these 14 nodes, you not requires exactly these 14 PMUs, but you need just 4 PMUs to know the voltages at each and every bus. If you know the complex bus voltage at each and every bus, then generally we'll say that system is observable. So in order to control the system, it should be observable. If you are able to observe the system, then only you can easily control the system, observability and controllability. Now we'll see other applications. So the conclusion from the state estimation is from olden SCADA system, unit takes time for like 2 to 3 minutes in the power system. Like earlier control centers used to take 1 minute or 30 seconds to run the state estimation to know the state of the system. But because of this PMU, they can directly see the directly they can measure the state of the system. What is the state of the system? So that's the advantage with the PMU. So you are avoiding that 30 seconds, 40 seconds to run your algorithm. So you're avoiding that, and you can see the you can directly measure the state of the system with the help of PMU. Now we'll see some what is the power system protection. We'll see what is the advantage of the PMU. You might have known in 2013 and 14, in the 2013 there is a all India blackout in the north western region and the northern region, there is 2 3 important lines are there, they got overloaded, and the one relay felt that overloading as a fault that is operated in zone 3. So because of that, the one line got tripped and the other line also got overloaded, and they are both important lines from northern region and western region. They are interlinking lines. Both got tripped, and that leads to the sequence of trippings, and that leads to the blackout in 2013. There is a uh, entire blackout of the grid. So the problem exactly that time identified is Zone 3 operation. Actually, Zone 3 should operate when Zone 1 protection is not operated. Here, Zone 1 means, for example, this is a B relay, C relay, A relay, and you can this relays. For B relay, this is a Zone 1 is 80% of the BC line. For D relay, the Zone 1 is 80% of the DE line. If Zone 1 fails, then relay A, Zone 3 will operate generally. But here you can see whenever in as I told in 2013, what happened is because of the overloading, the zone 3 failed. It is a fault, but it is a simply overload. It is not a fault because these two are not operated, and this one got operated. That leads to tripping. So using PMUs that can be avoided. Whether it will check whether zone 1 pick up in PMU B, PMU C, PMUD and PMU, whether zone 1 is pick up. If no, then it will blocks the zone 1, zone 3 of the relay A. So it will says the zone 1 of the B or zone 1 of D, no, zone 1 of the C or zone 1 of E is not operated. So here zone 3 should not operate. Now we'll go through some case studies. These are the actual data collected from PMU. So I'm taking the actual data to make you to understand. In 2004, this simple case studies we'll discuss. The complex complete outage of 400 by 220 kV Allahabad substation. 2012, 14th January, a bus fault happened at Allahabad, 400 kV bus. So this bus fault resulted in total loss of all the incoming and outgoing lines at this substation. You can see the exactly what happened at this substation. This data is taken from the real-time PMU. You can see the x-axis 5 hours 39 minutes 50 seconds and 000 milliseconds. So data is in the range of milliseconds. You can see here from 59,600 to yeah. Please, can you mute your mics, please? So you can see the accuracy of the data. Using this data, once the fault is occurred at around 539, 56, 55 seconds, all the three phase voltages are shifted by around 34 degrees. So all three phase voltages are moving. So it's simply a three phase fault. All three phase voltages are moving. This cannot be, you cannot see this from this SCADA because it reports every 4 seconds, whereas in this PMU it is in the range of milliseconds. You can see this how this voltage is varied, and you can easily tell what type of fault it is from seeing this all voltages. Now, detection of fault in neighboring grids. As I told, for postmortem analysis or to understand exactly from where the fault is initiated, so you need most accurate and high reporting data. Now we'll go through that. Detection of fault in neighboring grids. Three-phase fault occurred at 400 kV Bina in 22nd February in 2012, and you can see the how this voltage dip all the three phases, which indicate a three-phase fault at these Bina substations. Fault cleared in 540 milliseconds. So using this time, you can tell whether it is zone 1 operator, zone 2 operator, zone 3 operator using this time also. All these phase voltages are all together went down and all together went up. So it indicates your three-phase fault. Now we'll compute the system inertia of Indian power system using this fault data. So as I told earlier, normal common people think that the fault is bad, but system operators and simulators and researchers, they want some data from the fault to analyze the system behavior and to publish these papers also. So there are certain incidents and loss of generation 1580 occurred at Dadri NTPC complex in 2011, 10th July, 13 at afternoon. The rate of change of frequency is reported by the PMU is used for the calculation of the inertia. This new grid is like now we have a all India grid. In 2011, you have a synchronized grid of north, west, east, and northeast. That is called new grid. That time in 2011, southern grid is not synchronized with the northern grid or new grid. The all the northern regions, northwest and these regions are not connected with the southern regions, though they are connected with HVDC but not directly with AC lines. So that's why it is used new grid. Using this DF by DT, this after this fault, a loss of generation of 1580 megawatts at Dadri. Using this data, we can calculate the system inertia. As you know, inertia constant H is called PL by P into F naught. F naught is the initial frequency before the disturbance. PL is here is the generation loss, and P is the size of the new grid. Size of the new grid is around 65,300 that time, the installed capacity. And you got df by dt data from the PMU. So if you substitute this PL 1580 megawatts is the loss of generation by the size of the grid, what is the installed capacity or connected load at that time, total connected generation at that time, generation 65,300, and before the disturbance the frequency is 50.02. So if you multiply this 2 into df by dt data, you will get 7.5 seconds. This is the inertia constant of the Indian new grid at that time. And as you know, the system is so dynamic, it will changes from time to time. So this H value also varies from time to time, but not in the huge range, but in the range of 7 to 8 in the new grid in 2011. Now we'll go through some what are the different guidelines for this PMU installation in Indian grid. There is one problem we see in that we have a CA construction standards for 2012 which specifies the location of PMUs, and we have a URTDSM subcommittee report 2023 which gives the list of possible locations for PMU placement, and we also have CRC guidelines which tells exactly what are the parameters to be telemetered from the PMU from various substations, generating stations. So using this many system like many vendors or the states or PSUs, Power Grid and Grid India, or the power system developers, they all used to get confused and we used to ask questions. So we need to follow CA construction standards or URTDSM and CRC. There are certain each guidelines tells some certain slightly different things. So we formed a PMU committee in 2025. Our chairperson formed this committee in 2015 and given a task to bring uniformity along these three by taking these three guidelines. So finally, PMU committee to given a guidelines in 2015 by specifying the both optimal location where to place the PMUs and what are the signals to be telemetered from PMU to the control centers. So this committee guidelines are the final. Accordingly, uniformity in approach with respect of placement of PMUs in the Indian grid. Above committee guidelines 2012 shall be adapted for implementation. So now all will follow this PMU committee guidelines 2025 for placement of PMUs or in terms of what are the signals to be telemetered from PMU to the control center. So this committee given certain general requirements. Now just I will tell briefly so to understand what are the challenges and why we are given this general requirement. So to integrate these PMUs of different manufacturers, we need to follow the common standards. If you have common standards, then only you can integrate one PMU with other PMUs. Then we can transfer the same data to the control center. And there are, as you know, there is challenges, because if US withdraws this GPS, global position system, our PMU system will get failed. So our government given this mandate, and we also incorporated to use this NAVIC. As many of you know, it's a Indian GPS NAVIC, navigation with Indian constellation. So we recently NRLEC last year they had a piloted this. So instead of GPS, they used this NAVIC GPS NAVIC signals for synchronization. So in future, near future, in the general requirement of PMU also we mentioned this. It should be PMU for the future PMUs and present PMUs, and the upcoming manufacturer of PMUs are mandated with this condition that even in case of GPS signal is lost, they should immediately sync with lock with this NAVIC signal have to measure the real-time power system. So there is no problem even if GPS is withdrawn on the power system. Now we given others also, like we told PM shall support data reporting rates of 25 to 50 frames per second, because the more frames you will get the data, that's the more the accuracy. So basically PMS don't have any problems. The problems we are seeing is basically having the fiber network connectivity. So in the phase 2, we advised the power grid, even if that substation don't have fiber optic network, so please commission this fiber optic cable then and place the PMUs. Now it is mandated, and another thing is, now all the upcoming substation we mandated them to have the PMU. So in the upcoming under construction and the future substation will have compulsory PMU. They will install PMU at that in the substation. So these are the requirement. The PMU shall be able to acquire, measure, calculate at least the following signals, because as I told, each PMU can give you hundreds of data, but we told them at least this should be given, like A to I. We told that each PMU output should give at least these things, and above this, if the PMUs having giving the data, that's well and good, but we made it this is the minimum requirement that PMU should give the output. Three-phase are voltages, as I told earlier, magnitude and angle, three-phase current phasors, and positive sequence voltages, positive sequence currents, circuit breaker status, protection operated status, frequency, rate of change of frequency, and analog values. So these are the output of the PMU. And as I explained in the initial slides, the input to PMU is your CT, PT inputs from the substation, and GPS signal are the inputs to the PMU. So these are the criteria for PMU location. For example, I will you can get from the our reports, CA reports also. You can get this all these things. I will briefly explain few things. For example, earlier substation of 400 kV and above voltage, at one end of all transmission lines, you should have one PMO. Either, for example, if you take a 400 kV 400 kV transmission line from Ramagundam to Hyderabad, so you have an option to place one PMO at Ramagundam, or you can place a PMO at Hyderabad. But each 400 kV line should have one PMO either of the end, not compulsory to two ends, but on the one side of the 400 kV line. But we also made one more condition. For example, it is a inter-regional lines, then in that case you should have both sides, the PMU should have. What are the analog points? Voltage and currents. And digital points are the circuit breaker. And it also PMU takes the data from the this protection signals also. So we given these criteria for placement of PMUs, where the location, as you know, if you will place mostly will made compulsory placement of PMU at all these 400 upcoming substations, and we also made compulsory for like if, HV, for example, it is a HVDC substation. We made it is a compulsory, and we made compulsory for all important thermal generators of 100 and. Here you can see if it is generating station of 200 megawatt and above, we mandated that substation. If it is a hydro, it is 100 and above, we mandated to place PMO. If it is a gas and other we made it if it is, for example, it's a RE generating station, renewable energy like solar or wind, if it is 50 and megawatt and above, we mandated, because these are the critical infrastructure. We need to observe this data from this critical points. As I told, these are the HVDC substation or regenerating station, and also STATCOMs, FSC, TCSC, wherever this static controllers are there, we suggested them we mandated them to place this PMO, because these are the electronic devices. We want the data from them, their behavior during fault, and these are the critical components of the system. We want to monitor and we see the data for the next analysis purpose. And upcoming battery energy storage systems of 50 megawatt and above. And as I told, it's a inter-regional and transnational tie lines of 132 kV and above. As I told, you may get some ambiguity. As I told initially 400 kV, but now I'm saying 132 kV. It is very simple. 400 kV and above, you'll place PMU at one end of the line, and in general. But if it is an inter-regional line or transnational line, transnational means, for example, we have a line between India and Nepal, we have a line between India and Bhutan. So if it is of even 132 kV, you will place a PMU, because we want to see this. These are the critical lines of inter-regional or transnational lines where we need to, we want to observe that data. Accordingly, we suggest, we mandated them to place the PMUs at this. And some bulk consumers, wherever the important consumers are there, we suggest mandated them to place these PMS. So what are the challenges? As I told earlier, we have a huge data. So you need to you need some tools. So that tool should take the critical substation or the fault, wherever the fault comes, that substation, automatically that tool should select, and that display should be given to that particular substation, because you have 1400 PMUs. It is not practically possible to see 1400 PMUs data at the same time. So you need to select using this analytic tools only, you can see the exact data. And the reliability of synchrophasers, because this all PMUs are connected with communication network of optical fiber networks. So if fiber network is down, you will not get data from the synchrophaser. So this is one challenge we are facing. For example, if you take 100 PMUs, you will get data of 90 to 95 most of the time. At least 4 5 PMUs we are not getting data, because of the not PMU problem, but it's a communication problem we are seeing. And there is sometimes, because of the certain disturbances, we'll find some abnormal drift in spike in observed data, because of this some low this connection or interference with nearby some other data. And we are also facing certain issues like because you have huge data, it is a challenges in data retrieval from the historian. You have huge data, so how to retrieve the particular data. And also we are facing what data should be stored in the PDC, because if you store continuously 24 hours by 7, it becomes huge data. So there is we are proposing, we are working on this, what data should be exactly stored. For example, if any disturbance comes, that data should be compulsory, will be available for years. And if the system having no disturbance, so you can, after 2 months, after 3 months, you can remove that data. So we are working on it, because it's a continuous process. We are getting continuous challenges, and we are going through this. And As I told, this is a communication infrastructure we have in India. Will not have fiber network to all the substations. So we asked the power grid to have these PMUs wherever it is critical in nature. We asked to place PMU along with this communication, fiber optic communication. And the suggestions are like, as I told, what is there should be some threshold and operating limits for historical data. You cannot store hundreds of years of data, because you have a huge data, because of the it's in every millisecond it is reporting data to the control center. So you'll have huge data because of that speed and accuracy of the data. So there is a there should be some threshold, as I told earlier, for this historical data. Uh, and for example, if it is a major event, you should store for years. But if it is a system is running smooth without any major disturbance, then you should discard that data. So that you can optimally utilize this data servers. And we need to the suggestions like those intelligent alarms to alert the operators in real time, because as I told, huge data to where to give the attention is also matters. And storage synchronizer data, we are formulating the policy for storage of the synchrophaser we are working. And integration of PMU at national level. Why I'm saying this, now states also planning to place. Yeah, please, can anyone? So now comes to the conclusion. As I told, the synchrophaser technology has brought a paradigm shift from state estimation to state measurement. In olden days, using SCADA system will estimate the state, but now we are directly measuring the state. So there are many advantages in PMU in the real-time power systems. The major references are previous year reports and Grid India reports. Yeah, thank you. Thank you, Ananda. Kasi sir, please take.
Yes, sir. Thank you, sir. Thank you very much for your wonderful session, sir. So, dear participants, we request you to please ask the questions if you have any. Yeah, participants are requested to interact with our resource person.
A very good evening, sir.
Yeah, please.
Sir, it's very good informative session, sir. Sir, small doubt regarding the how fast we can eliminate the fault when PMU identify the differences in the phase angles and also. And generally, as you said in the last word, we need to transfer the data to the operator to remove the fault and all. With the help of PMU, how can we eliminate this in the time bound?
Yeah, basically in India, this project is, as of now, we are limited to not for the control action. PM is not for immediate real-time control action will not take, because the time the operator will not have that much time. By that time, the whatever happens, because already protection systems are in place. So before we taking the action, that automatically that respect to relays, respective circuit breakers will take the appropriate action. For example, any fault comes before we operate, because as an operator, if I see the fault and then I should operate, it takes at least minutes. But by that time, already relays will operate, and that respective circuit breaker will isolate. Basically, this PMU project is initial stage in India. It is not fully matured like in US. They will take the control actions. The output of the PM is to only to observe the at real time system, but not to take. For example, if the control action need to be taken in 10 seconds or 30 seconds, that will not be PM data. We are not able to do at present. But in future, like in US, there are advanced systems. The data will be directly optimized, and directly they given feed to the relays, and they give the output of the PMs to the certain controlled actuators that will control the directly. But we have the olden system of relays and circuit breakers which will operate before we take the action. The base major advantage of the PMUs is you can see and observe, and using this knowledge and experience, the next time we can plan the system accordingly. So it is mostly like offline application, I can say. Real time you can see, but by time you will take the action, already the system will take its own actions. You will not get much time to take the action.
Yes, sir. Thank you, sir. So that we can do the forecasting, load forecasting for the next generations. Sir. Is that right, sir?
Yeah. Not load forecasting. Load forecasting is different, but this is like you will understand the behavior of the system, and you can make your models validated. You can create your models most accurate. You can analyze from post-mortem of the fault, as I told, where exactly the fault started and what is the reasons, and you can do all this analysis from this system, this PMs.
Thank you, sir. Thank you very much, sir.
Yeah.
Thank you, sir. Any other participants? If you want to ask anything, please make utilize the opportunity. Sir, we have one question, sir.
Yeah, please, sir. Please, sir.
Sir, actually, you mentioned that the PMU can able to monitor the data from the far away thousands of kilometers. Means, is there any time lagging will be there, sir? Means in the system, every microseconds, milliseconds are somewhat precious. In that case, if we get any time lag, then what is the backup action that is available, sir?
Not much of lagging. Yes, data latency and data that will be there because of the optical cables, which is in the range of milliseconds only, not even in seconds. So I think you'll not get any problem because you're not taking real-time control system is not taking the data of PMU2 for the action. Already the relays and all control system components are prepared for already they are designed for to operate, when to not operate. So this data is we are not giving to relays or circuit breakers, so that have no impact on the system.
Okay, sir. Okay, sir. Thank you, sir. And one more, sir, if you are dealing with the big constraints of data, in India, we have one nation, one grid concept is there, no, sir?
Yes.
If there is a case, how safe is this data transmission can be happening, sir? Means we may have some cyber attacks, right? So do we have any such protection systems?
Yes, there is cyber always. If you open the door, you will get air and you will get some pollution also. So when you will get these technologies, you'll have cyber problems because of the technology, but you cannot avoid the technology. So as I told, and another thing I will tell in the other way, for example, you have even some cyber attack, you will get a few data of PM you will not get. But already your relays and circuit breakers and all other things, which are already designed how to behave for a fault. So, this will not impact the operation of the system. Real-time operation is depends on the if it is a fault happens already relays are there and circuit breakers are there, they will operate automatically. So this cyber impact will be not there because this control actions are not depends on the PMU data. The relay operation circuit breakers are not based as of now in India, I am telling. So the relay operation and circuit breaker operation is not based on the PMU data. PMU data we are seeing for our understanding, our analysis or modeling purpose.
Okay, sir. So means, sir, one situation when we got in COVID, sir, where once upon a time, on one day in the evening, the government of India has been initiated to switch off the lights, no, sir, loads. At the time, we heard that the frequency was raised to 51.5% and greater. So is that monitoring is also done by PMU, sir?
Yes, PMU data is there for generally in control center. They are using SCADA and PMU, both data they are using. For most accurate and to understand the oscillations like data or most accurate data, they are referring to PMU data. Or else they are seeing the this data. Whereas as you asked me about the frequency, rise of the frequency,
Yeah.
we already have some other
Yes, sir.
mechanisms to control the frequency. For example, when your
Okay, sir.
frequency crosses certain range, few generators will automatically using AGC, automatic generation control. It will give the signals to all the generator to reduce their generation. So you will get load generation balance and frequency comes to play. So there is no PMU role in that frequency control, but you can see the frequency using the PMU. You can see the what is the rate of change of frequency.
Okay, sir. Okay, sir. Thank you very much, sir. Thank you.
Yeah, thank you to
Any other
which
participants? Any other participants? If you have any questions, please interact. So, if you don't have any questions, sir, with your permission, can we close the session, sir?
Yes, thank you, Kasi sir, and thanks to Vishnu Institute for giving me this opportunity. Thank you, one and all.
So, thank you, sir. Thank you, sir. So, thank you very much, Sri Satish Kumar, sir, IES, for your highly informative and real-time presentation. Your explanation of PMU functionally, real-time data management, and grid optimization has provided the participants with valuable industry-oriented insights. So once again, thank you very much, sir, for accepting our invitation and being a part of this ATEL FTP. Thank you, sir.
Thank you, sir, for invitation. Thank you, one and all. Thank you.
Thank you, sir. Dear participants, so with this, we came to the end of another enriching day of our ATEL FTP. So on behalf of the organizing committee, I extend our heartfelt gratitude to both the today's eminent speakers, Dr. Narendra sir and Shri K. Satish Kumar sir, for their time, expertise, and impactful sessions. I also thank all the participants for your active engagement throughout provoking questions and consistent participant throughout these sessions. So tomorrow we'll be exploring the exciting topics on the power converters for microgrid by Dr. Mukesh Kumar Pathak sir, who is the chief guest of our FTP for inaugural session, and the next session by today's expert, Sri K. Satish Kumar sir, on condition monitoring and fault detection diagnosis with respect to wind energy conversion systems. So please make sure to join us in the on time as usual. So for the another simulating session. So with this, we'll be ending this today's session. So thank you all once again for joining the FTP on these sessions, for your continuous support. And thank you all once again and have a wonderful evening ahead. Thank you. You can leave the meeting.